When it comes to planets beyond our solar system, NASA has discovered worlds that defy normal expectations in astronomy. Some are extremely hot, extremely cold, or move around their stars in ways that are difficult to understand. Among these discoveries, there are a few planets that are especially difficult to explain, even for experienced scientists. This is not an ordinary planet of rock or gas located far away in space. It is a planet that challenges established ideas about how planets form and continue to exist. So, what makes planets strange? In this video, we'll take a journey to LTT 9779b, one of the most unusual planets ever found, and discover the secrets behind its dazzling brightness. Before we start our journey, drop it in the comments below where in the world you're watching from and what time it is there for you now. Now, get ready for a journey to the most unusual planets in the universe. K218b is an exoplanet orbiting a red dwarf star called K218. This star is located about 124 light-years away from Earth, which equals roughly 38 parsecs. The planet itself belongs to a category of worlds called sub-Neptunes, meaning that it is larger than Earth but smaller than Neptune. Its size is about 2 6/10 times the radius of Earth. K218b takes about 33 days to complete one orbit around its star. What makes it particularly fascinating is that its orbit lies inside the habitable zone of its star, a region where temperatures may allow liquid water to exist. Despite orbiting a much dimmer and cooler star, K218b receives almost the same amount of light as Earth does from the Sun. The exoplanet was first discovered with the Kepler Space Telescope, which was designed to hunt for planets beyond our solar system. Later on, the James Webb Space Telescope, often shortened as JWST, studied K218b in more detail to investigate its atmosphere. In the year 2019, scientists announced that water vapour had been detected in the atmosphere of K218b. This was a major discovery because water is essential for life as we know it, and the find immediately drew attention to this distant world. 4 years later, in the year 2023, the James Webb Space Telescope added more exciting details. It detected carbon dioxide and methane in the planet's atmosphere. These results sparked discussions among scientists about the nature of the planet. Some researchers suggested that K218b could be a water-rich planet covered by a thick hydrogen atmosphere, while others argued that it was more like a small version of Neptune filled mostly with gas. Then, in the year 2025, another surprising claim was made. Astronomers reported that they had found dimethyl sulfide, also called DMS, in the atmosphere of K218b. On Earth, this chemical is mostly produced by living organisms, especially by plankton in the oceans. The reported amount was about 20 times greater than what is found in Earth's atmosphere. Because DMS does not last long in the air, its presence would mean that something must be replenishing it. However, the discovery was met with skepticism. Ethan Siegel, a well-known astrophysicist, criticised the announcement, saying the claims were exaggerated and the analysis flawed. Other researchers pointed out that laboratory experiments show DMS can be produced without life. This means that while the detection is intriguing, it cannot yet be taken as solid proof of biological activity. The star K218 itself is a small red dwarf of spectral type M3v, located in the constellation of Leo. It is about 38 parsecs away, or 124 light-years from Earth. Compared with the Sun, K218 is smaller and colder. Its surface temperature is about 3,457 kelvins, which is roughly 3,184 degrees Celsius, or about 5,763 degrees Fahrenheit. Its radius is only about 45% of the Sun's radius. Because of its faintness, this star cannot be seen with the naked eye from Earth. Astronomers estimate its age to be around 2 4/10 billion years, with an uncertainty of about 600 million years. The star shows moderate activity, but scientists are not sure if it has star spots, which could sometimes interfere with measurements when planets pass in front of their stars. In addition to K218b, this star also has another planet called K218c, which orbits closer to the star and may influence K218b through tidal effects. Studies suggest that as many as 80% of all red dwarf stars might host planets inside their habitable zones. Examples of such stars include Proxima Centauri, TRAPPIST-1, and LHS 1140. Red dwarfs are attractive targets for planet hunting because their smaller size and lower temperatures make it easier to detect orbiting planets. Their planets usually orbit closely, meaning they pass in front of their star often, giving astronomers more chances to observe them. But there are also challenges. The faint light of these stars makes it harder to study planetary atmospheres with spectroscopic techniques, and red dwarfs are known to flare and show uneven surfaces, which can create false signals. K218b itself has a radius of about 2 6/10 times that of Earth, and a mass of about 8 6/10 times Earth's mass. The planet completes one orbit in about 33 days, and can be observed from Earth when it passes in front of its star. Astronomers believe it is probably tidally locked, meaning one side always faces its star, just as the Moon always shows the same face to Earth. However, there is also the possibility that its rotation is in a resonance, similar to Mercury in our solar system. The density of K218b is about 2 6700 grams per cubic centimetre. This is between the density of Earth and that of Neptune, which suggests the planet has a thick hydrogen-rich atmosphere. It may either be a rocky planet with a deep atmosphere, or one with a Neptune-like composition. A pure water world with only a thin atmosphere is less likely. Interestingly, planets with radii around 1.5 to 2 times that of Earth are rare compared with what scientists expect. This gap is called the radius valley. It is thought that planets of this size often lose their atmospheres due to the energy from their stars or from their own heat. Smaller planets in this range tend to become super-Earths, while larger ones tend to be classified as sub-Neptunes. Scientists believe K218b may have taken a few million years to form. Tidal heating is not expected to play a major role in its temperature. While there may be internal heating deep inside, it is unlikely to affect the surface much. If the planet has an ocean, it may be covered by a layer of high-pressure ice lying above a rocky core. This structure could prevent mixing between the ocean and the core, which might affect the planet's climate and habitability. At very high temperatures above the so-called critical point, the difference between liquids and gases disappears, so there is no longer a clear separation between ocean and atmosphere. Whether K218b has a distinct liquid ocean is still unknown. Detecting such an ocean from so far away is extremely difficult, and current observations cannot give a clear answer. Before the James Webb Space Telescope collected its data, scientists thought that water on K218b was more likely to be in a supercritical state, a form that is neither purely liquid nor gas. JWST's results, however, appeared to suggest the possibility of a liquid ocean beneath the atmosphere. Certain gases, such as ammonia and hydrocarbons, can dissolve into an ocean if one exists, so their presence or absence can give clues about whether a surface ocean is there. Some later studies argued that a magma ocean could also explain the observations, though this would not match the levels of carbon dioxide that were detected. Other research suggested that to explain the methane levels seen, a biosphere, some form of life, would be needed, yet this remains highly speculative and far from proven. Observations made with the Hubble Space Telescope have shown that the exoplanet K218b has an atmosphere that mainly consists of hydrogen. Scientists also believe that water vapour could be present in this atmosphere, but the evidence is not yet certain. The James Webb Space Telescope has suggested that the amount of water vapour might be very small, less than 1/10%. This low reading may be because the James Webb Telescope is seeing a dry upper layer of the atmosphere, called the stratosphere, which is kept that way by a process known as a cold trap that prevents water from rising higher. Measurements also show that the amount of ammonia in the atmosphere is extremely low, so low that it cannot be properly measured. However, the James Webb Telescope has detected that methane and carbon dioxide each make up about 1% of the atmosphere. Other carbon-based gases have not been clearly detected, but their concentration is estimated to be only a few percent at most. Overall, the entire atmosphere of K218b makes up no more than 6.2% of the planet's total mass, and its mixture of gases is thought to be similar to the atmospheres of Uranus and Neptune in our own solar system. So far, there is little sign of hazes in the atmosphere. When it comes to clouds, the evidence is unclear. If clouds do exist on K218b, they would most likely be made of ice, although liquid water clouds could also be possible. Apart from water-based clouds, other kinds of clouds could form depending on the planet's conditions. These include clouds made of ammonium chloride, sodium sulfide, potassium chloride, and zinc sulfide. Most computer models also suggest that the planet should have a stratosphere caused by a temperature inversion high in the atmosphere. The star K218, which the planet orbits, sends out powerful radiation such as ultraviolet rays and X-rays. These high-energy rays heat the upper layers of the planet's atmosphere. They also break apart water molecules, creating hydrogen gas that rises and forms a very large outer layer called an exosphere. This hydrogen-rich exosphere slowly escapes into space. The amount of ultraviolet and X-ray radiation that K218b receives is much stronger than what Earth receives from the Sun. Because of this, the exosphere escapes into space at an estimated rate of around 350 tons every second. Even though this may sound like a huge amount, it is not fast enough to remove the whole atmosphere of the planet over its lifetime. There are also hints of this exosphere being detected through changes in the planet's Lyman alpha radiation during its transits across the star, though these findings still need to be confirmed by further studies. Detecting atmospheres around planets outside our solar system is always difficult, and some of the reported results about K218b remain debated among scientists. For example, in the year 2021, Barclay and colleagues suggested that the water vapour signal might not actually be water at all, but could instead be caused by the activity of the star itself. Earlier, in the year 2020, Bizarre and other researchers proposed that methane could make up between 3 and 10% of the atmosphere, while water might make up between 5 and 11%. Later, in the year 2022, Bizarre, Charnay and Blaine suggested that what looked like water in the data might actually be caused by methane, although they admitted that this explanation is less likely. To understand the possible climate of K218b, scientists have used many computer models. Some of these studies are part of a larger project known as Camembert, which compares the climates of planets similar to K218b. One study by Charnay and colleagues in the year 2021 assumed that the planet is tidally locked, meaning that one side always faces the star while the other side is always in darkness. Their model showed that the atmosphere would have only weak differences in temperature between different regions. They also predicted a wind system where air sinks on the night side and rises on the day side. In the upper atmosphere, methane absorbs radiation and creates a layer where the temperature increases with height. Clouds could only form if the atmosphere had a high concentration of heavy elements. These clouds would strongly depend on the size of cloud particles, the composition of the atmosphere and how the winds circulate. The clouds would mostly appear at the substellar point, which is the spot directly under the star, and along the terminator, the line dividing day and night. If rain formed in these clouds, it would not reach the surface but instead would evaporate in midair, forming what is called virga. The researchers also ran simulations where the planet's spin and orbit interacted differently, but this did not change the distribution of clouds much. They even modelled how the atmosphere would look when the planet passes in front of its star. Another study by Innes and Pierre Humbert in the year 2022 tested different possible rotation speeds of the planet. They found that unless the rotation was extremely fast, there would not be large temperature differences between the poles and the equator. Their model also showed jet streams near the equator and at high latitudes, with weaker jet streams closer to the surface at the equator. In the year 2021, Hu created models focused on the chemistry of the planet's atmosphere. He found that photochemistry alone should not completely remove ammonia from the outer atmosphere. He also predicted that carbon oxides and cyanide would likely form in the middle layers of the atmosphere, where they might be detected in future studies. His model suggested that a haze made of sulfur could appear, stretching through and above the water clouds, making it harder to investigate the atmosphere directly. More recently, in the year 2024, Tsai and his team ran detailed chemical and physical models. They discovered a strong eastward jet stream in the lower atmosphere, called the troposphere, and a westward jet stream above at very low pressures. Between these two layers, the circulation was driven by heat. They also reported a possible detection of dimethyl sulfide, a molecule that on Earth is often linked to biological activity. However, the signal could easily be hidden by other hydrocarbon gases, and for dimethyl sulfide to be noticeable, it would need to be produced at a rate about 20 times higher than what occurs on Earth. Such a high rate is possible if the planet had some form of ecosystem. The amount of starlight that reaches the planet K218b has been measured at about 1,368 watts per square metre, with a possible variation of a little over 100 in either direction. This is very similar to the amount of sunlight that reaches Earth on average. Because of this, the planet sits within, or just slightly inside the so-called habitable zone of its parent star. This is the region around a star where conditions might allow liquid water to exist. Scientists think K218b may lie close to the point where a runaway greenhouse effect could occur, but not quite reach it. If we imagine the planet without any greenhouse gases in its atmosphere, its surface temperature would probably be somewhere between about 250 Kelvin, which equals about minus 23 degrees Celsius, or minus 10 degrees Fahrenheit, and 300 Kelvin, which equals about 27 degrees Celsius, or about 80 degrees Fahrenheit. Whether K218b is truly habitable depends on several factors: the type and thickness of its atmosphere, how reflective its clouds and hazes are, and how heat is distributed at different layers. Deeper layers of the atmosphere may actually be far too hot, while the upper water-containing layers could, though not with certainty, have the right combination of temperature and pressure to allow life to appear. Experiments on Earth have shown that microorganisms are able to survive even in atmospheres dominated by hydrogen, which means hydrogen itself is not a barrier to life. But there is a complication. Many of the chemical gases that scientists normally use to identify life, called biosignatures, do not behave reliably in hydrogen-rich atmospheres. This means that researchers would need to look for different chemical signs if they hope to find evidence of living processes on K218b. A study by Niku Madhusudan and his colleagues suggested that some of these markers could indeed be detected by the James Webb Space Telescope if enough observations are collected. The planet itself was first discovered in the year 2015 by NASA's Kepler Space Telescope. Its existence was later confirmed using the Spitzer Space Telescope and also through measurements of its host star's wobble, known as the Doppler velocity method. Careful analysis of the planet's transits across its star ruled out other explanations, such as hidden companion stars or multiple planets causing misleading signals. At first, estimates of the star's radius were inaccurate, which meant the radius of the planet was miscalculated and its density was believed to be greater than it actually is. In the year 2019, scientists detected the signature of water vapour in the planet's atmosphere. This was the first time water vapour had ever been detected on an exoplanet that was not a hot Jupiter, and the discovery created a wave of excitement and debate in the scientific community. K218b has since become a kind of test planet for exoplanet studies. Its unusual characteristics have led to the introduction of a new planetary category called a Hycean planet. These are worlds thought to contain both large amounts of liquid water and a surrounding hydrogen atmosphere. Before K218b, such planets were thought to be far too hot to support life, but observations suggested that some of them might actually be cool enough to host liquid oceans. The thick hydrogen blanket acts like a powerful greenhouse layer, which could help these planets stay warm enough to remain habitable, even when they receive relatively little starlight. Today, K218b is probably the most famous example of a Hycean planet, although scientists also consider other possible compositions, some of which could allow habitability while others would not. Adding to the intrigue, evidence has been reported for the presence of certain molecules in its atmosphere, including dimethyl sulfide, DMS, and methyl chloride. On Earth, nearly all of the DMS in the atmosphere comes from tiny marine organisms called phytoplankton. Because of this, DMS has been considered a potential biosignature gas. However, scientists stress the need for much more data before drawing conclusions, since DMS can also be created by non-biological processes. In fact, some experts have warned that the statistical evidence for DMS on K218b is weak and may not hold up in future analyses. In January of the year 2024, NASA astrophysicist Nicole Colon spoke about James Webb Space Telescope observations of K218b on a Planetary Society podcast. She explained that the telescope's MIRI instrument would soon collect more data that could help confirm or refute the presence of certain molecules. At the same time, she pointed out that Webb's data did not show strong evidence of water in the atmosphere, which raised new questions. Later that year, in April, the telescope carried out 2 long observations lasting more than 8 hours each. In April of the year 2025, the same research team that had earlier reported possible DMS again claimed a detection of DMC, or a related compound called DMDS, this time with a 3 sigma statistical significance. The announcement came with a press release stating it was the strongest hints yet of biological activity outside the solar system. This bold claim was quickly met with criticism. NASA reminded the public that detecting a single molecule could not, by itself, prove the existence of life. Other scientists pointed out that laboratory studies show DMS can form without biology being involved. Later studies even suggested that other gases, such as propine, a compound known to exist on Neptune, might explain the telescope's observations more accurately. Ongoing research has also debated whether the signals attributed to DMS are even statistically meaningful. Some studies suggested that no strong evidence for DMS or any other specific gas exists in the available data. Others have argued that when all the data and hundreds of possible gases are considered, DMS remains one of only a few molecules that could explain the signals seen. Interestingly, the other candidates include two much more complex molecules, diethyl sulfide and methacrylonitrile, neither of which have known non-biological sources in planetary atmospheres. Even so, more recent analyses, combining data from several James Webb instruments, found little to no convincing evidence of DMS. These studies pointed out that to settle the question, many more observations, possibly as many as 25 separate planetary transits, would be required. In the year 2025, new research with 4 additional transits suggested that the planet may have a water-rich interior, but that the small amounts of DMS and methylmercaptan that were hinted at could be explained without the need for life. Some scientists concluded that no DMS was present at all. WASP-12b is what astronomers call a hot Jupiter, which means it belongs to a class of giant planets outside our solar system that are similar in size to Jupiter, but orbit extremely close to their parent stars. This unusual world orbits the star known as WASP-12, and was first discovered in April of the year 2008 by the Super-WASP Planetary Transit Survey. Unlike Earth, which takes about 365 1/4 days to complete a single trip around the Sun, WASP-12 circles its star in just a little more than 1 Earth day. The distance between this planet and its star is about 3.5 million kilometres, which is equal to around 2.2 million miles, or 0.023 astronomical units. To put that in perspective, this is only about 143rd of the distance between Earth and the Sun. Its orbit has an eccentricity similar to that of Jupiter in our own solar system. Because of how close it lies to its blazing star, the planet has one of the lowest densities of all known exoplanets, a condition that scientists describe as inflated due to the intense energy pouring onto it. On the 3rd of December in the year 2013, scientists using the Hubble Space Telescope announced that they had detected water in the atmosphere of this strange world. The following year, in July of 2014, NASA reported that WASP-12b and 2 other exoplanets, HD 189733b and HD 290458b, had very dry atmospheres despite orbiting stars much like the Sun. In September of 2017, another team using the Hubble telescope found that WASP-12b reflects only about 6% of the light that falls on it. For this reason, astronomers have described it as being as black as asphalt, or pitch black. Yet despite this darkness, it still glows faintly with a reddish heat because its surface is extremely hot. Like other hot Jupiters, WASP-12b is tidally locked. This means that one side of the planet always faces its star in constant daylight, while the other side is trapped in eternal night, just as the same face of the moon always looks toward Earth. The contrast in heating between the two sides causes massive flows of heat, and generates violent winds racing through its atmosphere. Researchers Taylor Bell and Nicholas Cowan suggested that hydrogen atoms on the scorching day side become ionized, and when the winds carry them to the cooler night side, they recombine into neutral atoms again. This cycle of ionization and recombination helps transport heat more efficiently across the planet. The gravitational pull between the star and the planet is so strong that WASP-12b is being stretched into the shape of a prolix spheroid, rather than a perfect sphere. Its atmosphere is also being stripped away at an astonishing rate of about 189 quadrillion tons per year, or about 6 billion tons every second. This enormous loss of material, combined with tidal heating and its closeness to its star, pushes the planet's surface temperature above 2,500 Kelvin, which equals about 2,200 degrees Celsius. On the 20th of May, in the year 2010, the Hubble telescope captured evidence showing that WASP-12b was actually being consumed by its star. While scientists had long theorized that stars could swallow planets, this was the first time such a process was directly observed. Astronomers estimate that the planet may only survive for another 3 to 10 million years before it completely disappears. Observations of WASP-12b were carried out with Hubble's Cosmic Origins spectrograph. These confirmed predictions published earlier, in February of 2009 by Shulin Lee of Peking University. The planet's atmosphere has ballooned to nearly 3 times the radius of Jupiter. Even though it is so bloated, it still contains about 40% more mass than Jupiter. In 2012, researchers using the Rossiter-McLaughlin effect discovered that the orbit of WASP-12b is strongly misaligned with the equatorial plane of its star, tilted by about 59 degrees, give or take some uncertainty. Another important finding came in 2019, when scientists realized that the time between each orbit, or transit, was shrinking. Since its discovery in 2008, the orbital period has been decreasing by around 29 milliseconds per year. In 2020, that figure was updated to about 32.5 milliseconds per year. This meant that the planet's estimated lifetime had dropped to only about 2.9 million years. In 2022, scientists refined this number again to just under 30 milliseconds per year, giving the planet a new estimated lifetime of roughly 3.16 million years. The conclusion was that WASP-12b's orbit is slowly decaying because of tidal interactions with its parent star, pulling the planet ever closer until it will one day merge with the star. The decay is happening much faster than what has been seen in another hot Jupiter, WASP-19b, which so far shows no orbital decay. Back in 2010, another study revealed that WASP-12b has an unusually high carbon-to-oxygen ratio in its atmosphere, much higher than that of our Sun. While the Sun has a carbon-to-oxygen ratio of about 0.54, WASP-12b's ratio is closer to 1. This indicates that it is a carbon-rich gas giant. One of the scientists involved remarked that if there is more carbon than oxygen, the planet could form rocks made almost entirely of carbon, like diamond or graphite. This led the media to nickname WASP-12b the Diamond Planet. The carbon in its atmosphere exists in the form of carbon monoxide and methane, and the results of this study were published in the journal Nature. The possibility of carbon-rich planets also suggests that small, rocky worlds made mostly of carbon might exist, with interiors made of graphite or diamond rather than silicate rock like Earth. Russian astronomers studying changes in the brightness of the planet noticed a regular variation that could mean there is a plasma torus surrounding a possible exomoon orbiting WASP-12b. This would be highly unusual, since hot Jupiters are not expected to hold on to large moons for long geological timescales. If it is not a moon, the object could instead be a Trojan body, an object that shares the same orbit as the planet. Janssen, also known as 55 Cancri e, is one of the most fascinating exoplanets discovered so far. It orbits a star called 55 Cancri a, which is a star very similar to our own Sun. This planet is quite massive for a rocky world. Its weight is about 8 times greater than that of the Earth, and its diameter is about twice as wide as Earth's. The planet was officially discovered on the 30th of August in the year 2004. This discovery was groundbreaking because Janssen became the very first super-Earth ever found around a star that is still on the main sequence, meaning a star still burning hydrogen in its core like our Sun. This historic find actually happened 1 full year before the detection of another famous super-Earth. Gliese 876d Janssen is the closest planet to its star in its system, orbiting so tightly that it completes a full circle around the star in less than 18 hours. Originally, scientists thought it needed about 2.8 days to finish one orbit, but better observations and recalculations in the year 2010 revealed the true orbital period was much shorter. Because it lies so close to its parent star, Janssen is unimaginably hot. On the side that faces the star, temperatures can rise to well over 3000 Kelvin. That is hot enough to melt many metals. Interestingly, scientists noticed that the planet's thermal radiation changes over time, which may be a sign of active volcanoes on its surface. Some researchers have even suggested that this strange world could be a carbon planet, made mostly of carbon-rich materials instead of the oxygen-rich rocks that form Earth and its neighbours. The atmosphere of Janssen has been the subject of many studies. At first, astronomers thought it had an atmosphere filled with hydrogen and helium, much like Neptune or Jupiter. Later, however, observations did not support this idea. Instead, it looked more likely that the atmosphere contained heavier molecules, possibly just a very thin layer of vaporized rock. But in the year 2024, new measurements from the James Webb Space Telescope ruled out the idea of a rock vapour atmosphere. Instead, they gave strong evidence that Janssen has a thicker atmosphere, rich in gases such as carbon dioxide or carbon monoxide. In July of the year 2014, the International Astronomical Union, also known as the IAU, started the Name Exoworlds project, which allowed the public to choose proper names for selected exoplanets and their stars. People could suggest names and vote for their favourites. In December of the year 2015, the IAU announced the winning name for 55 Cancri E was Janssen. The name was proposed by the Royal Netherlands Association for Meteorology and Astronomy. It was chosen to honour Zacharias Janssen, a spectacle maker from the Netherlands who is often credited with helping to invent the telescope. Like many other exoplanets discovered before NASA's famous Kepler mission, Janssen was first found using the radial velocity method. Astronomers carefully studied the spectrum of light from 55 Cancri A and measured tiny changes caused by the star's motion, a motion created by the gravitational pull of its planets. At the time, 3 other planets were already known around the star. After accounting for their influence, astronomers still saw an unexplained signal at a period of about 2.8 days. This suggested the presence of another planet with at least 14 Earth masses orbiting very close to the star. The same measurements also confirmed the existence of another planet in the system, called 55 Cancri C. Janssen was one of the very first exoplanets discovered with a mass similar to that of Neptune. It was announced at the same time as another so-called hot Neptune, Gliese 436b, which orbits a red dwarf star. However, the existence of Janssen was briefly doubted. In 2005, researcher Jack Wisdom reanalyzed the data and argued that the supposed 2.8-day orbit might actually be an illusion, or alias. He also suggested that there might instead be a planet with a much longer orbit of 260 days. A few years later, in 2008, a new analysis by Deborah Fisher and her team appeared to confirm both the 2.8-day planet and the 260-day planet. But in the year 2010, astronomers Sarah Dawson and Daniel Fabricki showed that the 2.8-day period was indeed an alias, and that Janssen's true orbital period was less than a single day, about 0.7365 days, or around 18 hours. On the 27th of April in the year 2011, astronomers confirmed that Janssen passes directly in front of its star, creating a transit. This was observed after 2 weeks of nearly constant monitoring by the Canadian space telescope called MOST. The transit matched perfectly with the orbital period predicted by Dawson and Fabricki. Such transits are rare around bright stars and provided a unique chance to study the planet's size, density, and atmosphere in greater detail. Janssen is extremely close to its star, at an average distance of only 0.0154 astronomical units, which is many times closer than Mercury is to the Sun. This tight orbit means the planet is most likely tidally locked. One side, the day side, always faces the star and remains blazing hot, while the other side, the night side, is in permanent darkness. The planet's temperature is extreme. The day side reaches more than 2000 Kelvin, about 1700 degrees Celsius, which is more than 3100 degrees Fahrenheit, hot enough to melt iron. Early observations with the Spitzer Space Telescope showed the average dayside temperature to be about 2700 Kelvin, or 2430 degrees Celsius. The night side was much cooler, at around 1380 Kelvin, or about 1110 degrees Celsius. But a reanalysis of Spitzer data in the year 2022 found even higher dayside temperatures, about 3770 Kelvin, equal to 3500 degrees Celsius, and set an upper limit of about 1650 Kelvin on the night side. When Janssen was first discovered, scientists were unsure whether it was a small gas giant like Neptune or a large rocky planet like Earth. The confirmation of its transit in 2011 allowed researchers to calculate its density. At first, some thought it might be a water world, but the absence of hydrogen signatures during transit suggested that its main volatile substance could be carbon dioxide rather than water or hydrogen. Another fascinating possibility is that Janssen is a carbon-rich rocky planet, unlike Earth, which is made mostly of oxygen-rich rocks. If true, then as much as 1/3 of the planet's entire mass could be carbon. Under the high temperatures and pressures deep inside the planet, Some of this carbon could exist in the form of diamonds. If so, Janssen would truly be a diamond planet. More studies are still needed to confirm its exact nature, but it remains one of the most intriguing exoplanets known to science. One idea put forward by scientists is that a mix of different forces, tidal forces from the nearby star, along with orbital and rotational centrifugal forces, could help trap a hydrogen-rich atmosphere on the dark side of the planet, the side that never sees the star. If we imagine the atmosphere being made mostly of gases released by volcanic activity, together with a large amount of hydrogen, the heavier gases could remain trapped close to the planet, especially within latitudes below 80 degrees. The lighter and more restless hydrogen, however, would not be held in place so easily. Instead, it would slowly leak or drift toward the day side of the planet, where the powerful blasts of X-rays and ultraviolet light from the star would break it apart and destroy it. For this process to actually work, the planet, known as 55 Cancri E, would have had to become tidally locked early in its history, before it lost all of its hydrogen atmosphere. This explanation matches with certain spectroscopic observations that claim to detect hydrogen around the planet, as well as with other studies that did not find any clear evidence that hydrogen was being destroyed at a high rate. In February of the year 2016, NASA announced a major discovery made with the Hubble Space Telescope. The telescope had detected hydrogen cyanide in the atmosphere of 55 Cancri E, but it did not detect any water vapour. This finding suggested that the planet's atmosphere must be made mostly of hydrogen or helium. It was a landmark achievement because it was the very first time scientists had been able to successfully study the atmosphere of a super-Earth exoplanet. Later, in November of the year 2017, new results came from the Spitzer Space Telescope, which observed the planet in infrared light. These observations hinted that 55 Cancri E might be covered by a global ocean of molten rock, hidden beneath an atmosphere with a pressure of about 1 4/10 bar, slightly denser than Earth's own atmosphere. This atmosphere might even contain familiar gases such as nitrogen, and perhaps even oxygen, in order to produce the unusual infrared signals that Spitzer recorded. However, these results were not entirely consistent with earlier findings. For example, a spectroscopic study in the year 2012 did not detect hydrogen escaping from the planet, and another study in the year 2020 also failed to detect helium escaping. These results suggest that the planet might not have its original hydrogen or helium atmosphere anymore. Still, this does not completely rule out the possibility that 55 Cancri E could have an atmosphere made of heavier gases like nitrogen or oxygen. More recently, in May of the year 2024, astronomers used the James Webb Space Telescope to take an even closer look at 55 Cancri E. With its advanced near-infrared camera and mid-infrared instrument, they produced a thermal emission spectrum of the planet, studying its heat signature in the range of 4 to 12 micrometers. These measurements disproved the earlier idea that the planet was simply a lava world surrounded by a thin atmosphere of vaporized rock. Instead, they showed clear evidence for a real, substantial atmosphere rich in volatile gases, most likely carbon dioxide or carbon monoxide. The researchers suggested that the planet's vast ocean of magma might be releasing gases into the air, constantly replenishing and maintaining this atmosphere. Another set of strange observations has revealed that the planet experiences large variations in surface temperature. These swings could be explained by volcanic eruptions blasting massive clouds of dust into the atmosphere. Such dust clouds would blanket the planet, trap heat, and block its thermal radiation from escaping into space. By the year 2022, astronomers had also noticed major changes in the depth of the planet's transits. That is, the tiny dips in starlight as the planet passes in front of its star. These variations might be caused by giant volcanic events, or possibly by a ring-shaped cloud of gas, known as a torus, moving along with the planet in its orbit. Because 55 Cancri orbits extremely close to its star, less than 1/10 of an astronomical unit, some scientists have wondered whether its presence might even trigger flares on the star itself. These flares, in theory, could be synchronized with the planet's orbit through strong magnetic interactions. Back in the year 2011, astronomers carried out a search for such magnetic interactions by looking for radio signals from the star's outer atmosphere or corona, but no signals were detected, leaving the question open. TRIS-2b, also called Kepler-1b or GSC 03549-02811b, is a planet outside our solar system that circles around the star known as GSC 03549-02811. This star is located about 750 light-years away from Earth. The planet became famous in the year 2011, when astronomers identified it as the darkest exoplanet ever found. It reflects less than 1% of the light that falls on it. To give a sense of how dark it is, TRESS 2b reflects even less light than charcoal or coal dust, meaning that to the human eye its surface would appear almost completely black. However, because it lies so close to its parent star, the planet still shines with a very high brightness in space, glowing not from reflection, but from the intense heat it receives. The measurements of its size and weight show that TRESS 2b is a gas giant, much like Jupiter in our solar system. But unlike Jupiter, which is far away from the Sun, TRESS 2b orbits extremely close to its host star. This makes it part of the family of exoplanets that astronomers call hot Jupiters, giant planets with searingly hot atmospheres caused by their tight orbits. This star system lies within the field of view of the Kepler Space Telescope, which later provided even more detailed observations, but long before Kepler, TRESS 2b had already attracted attention. The story of its discovery began on August 21, 2006, when astronomers working on the Transatlantic Exoplanet Survey, abbreviated as TREE, spotted the planet. They detected it by observing the tiny dimming of its star whenever the planet passed directly in front of it, a method known as the transit method. The discovery was made using small telescopes, only about 10 centimeters wide, called Sleuth at the Palomar Observatory in California and PSST at the Lowell Observatory in Arizona. A few weeks later, on September 8, 2006, the finding was confirmed at the W.M. Keck Observatory in Hawaii, this time by measuring the star's radial velocity, which showed the slight gravitational pull caused by the planet. More work followed. In the year 2007, researchers improved the estimates for the planet's and the star's properties. Then, in the year 2008, another study revealed something remarkable, that the TRESS 2 system is actually a binary star system. This discovery meant that astronomers had to revise their measurements, since having two stars instead of one changes the way the planet's orbit and its properties are understood. Later that same year, more precise observations showed that the orbit of TRESS 2b is tilted by about -9 degrees, give or take 12 degrees, relative to the star's equator. The planet orbits in the same direction that the star spins, which is called a prograde orbit. In March 2009, NASA launched the Kepler spacecraft, a telescope built specifically to find new planets by the transit method. Just 1 month later, in April 2009, Kepler sent back its first images, known as its first light. Out of all the objects in its view, TRESS 2b was chosen as one of only 2 examples to highlight in these first images. It was not the only exoplanet in the telescope's field of vision, but it was the only one clearly shown in that initial release. This gave TRESS 2b an important role as a kind of calibration planet, used to check the accuracy of the spacecraft's instruments. Kepler's observations added new layers of understanding. Astronomers were able to confirm the planet's mass not only through transit dips, but also by analysing subtle changes in the brightness of its host star. These brightness variations came from several effects: the gravitational tug of TRESS 2b slightly distorting the shape of the star, and tiny changes in light caused by Doppler beaming, a shift in brightness due to the motion of the star. Then came the most dramatic result. In the year 2011, data from Kepler revealed that TRESS 2b has an astonishingly low albedo, the scientific word for reflectivity. Its geometric albedo was measured at only about 0.04%, making it the darkest planet ever discovered. For comparison, even coal or black acrylic paint reflects more light than TRESS 2b. Scientists estimated that its true albedo is less than 1%, far below what had been seen for any other planet. The reasons for this extreme darkness remain a mystery. One explanation is that TRESS 2b simply lacks the reflective clouds that make Jupiter shine so brightly. Its closeness to the star heats the planet to such high temperatures that clouds of bright particles cannot form. Instead, its atmosphere may contain chemicals that actively absorb light, such as vaporized sodium and potassium, or perhaps gaseous titanium oxide. However, some models rule out heavy compounds like oxides of titanium and vanadium, since it is unlikely they would remain in the upper atmosphere. More broadly, Scientists point out that hot Jupiters in general tend to be dark since sodium and potassium strongly absorb visible light. The only major exception so far is another hot Jupiter called Kepler 7b, which has an unusually high reflectivity of around 38%, plus or minus 12%. TRAPPIST 2b is also thought to be tidally locked to its star, meaning one side of the planet always faces the star in perpetual daylight, while the other side remains in endless night. In the year 2015, astronomers estimated that the temperature on the dark night side of the planet is still a blistering 1,885 kelvins, with an uncertainty range of about plus 51 and minus 66 kelvins. To put that in perspective, this is hotter than molten lava on Earth. Even after many years, TRAPPIST 2b continues to fascinate astronomers. Its strange, light-absorbing atmosphere and its nearly pitch-black appearance make it one of the most mysterious planets ever studied. Each new observation sharpens the picture, but also deepens the puzzle of why this world is so dark. Proxima Centauri b is an exoplanet that orbits within the so-called habitable zone of the red dwarf star Proxima Centauri, located in the constellation of Centaurus. This planet is also called Proxima b or Alpha Centauri cb. Its parent star, Proxima Centauri, is the closest star to our Sun. It lies at a distance of about 4.2 light-years, or about 1.3 parsecs from Earth, making it part of the well-known triple star system Alpha Centauri. Within this system, Proxima b and Proxima d, together with the debated candidate planet Proxima c, are the nearest exoplanets ever discovered outside our solar system. Proxima Centauri b travels around its star at a very close distance, only about 0.048 astronomical units, which is around 7,253,000 kilometers, or roughly 4,506,000 miles. The planet completes one full orbit in just a little more than 11 Earth days. By comparison, Earth takes about 365 days to circle the Sun. As of the year 2025, scientists know only a limited amount about the physical nature of Proxima Centauri b. Most evidence suggests that it is a rocky, Earth-like planet. Its minimum estimated mass is about 1.06 times that of Earth, and it may also be slightly larger in radius. However, whether or not the planet has an atmosphere is still uncertain, and this factor is crucial for determining if it could support life. One of the challenges is that Proxima Centauri is a flare star, frequently blasting intense radiation into space. Such outbursts could strip away any atmosphere the planet might have, making habitability less likely. The discovery of Proxima Centauri b was announced on the 24th of August in the year 2016 by the European Southern Observatory. The planet was confirmed after several years of Doppler spectroscopy observations of the star. Its detection was celebrated as a groundbreaking moment in planetary science, and immediately drew worldwide attention to the Alpha Centauri system. By the year 2023, Proxima Centauri b had become the most widely known exoplanet to the general public, mainly because of its closeness to Earth, which raises hopes that one day robotic probes could be sent there. Long before its discovery, astronomers had already targeted Proxima Centauri in their search for exoplanets. Early studies in the years 2008 and 2009 had ruled out the presence of very large planets in its habitable zone. Statistically, small planets are quite common around red dwarf stars. On average, each dwarf star is expected to host between 1 and 2 planets, and about 20 to 40% of red dwarfs may have planets lying in the habitable zone. This is especially significant since red dwarfs are the most common type of stars in the entire galaxy. Before the year 2016, data from telescopes at the European Southern Observatory in Chile revealed unusual wobbles in Proxima Centauri's motion that could not be explained by normal stellar activity such as flares. This suggested the presence of an orbiting planet. In January of that same year, a group of astronomers launched the Pale Red Dot project with the aim of confirming this hidden world. On the 24th of August 2016, the team, led by Guillem Anglada Escudé, officially announced the discovery of Proxima Centauri b. The Proxima system has revealed more surprises since then. In the year 2022, astronomers confirmed the existence of another planet, Proxima Centauri d, which orbits even closer to the star. A third candidate, Proxima Centauri c, was reported in the year 2020, but its existence remains disputed, as the signals may have been caused by data errors, Some reports have also suggested a dusty belt of material around Proxima Centauri, but this too remains unconfirmed. Proxima Centauri b is about 20 times closer to its star than Earth is to the Sun. Its orbit takes roughly 11.185 Earth days. As of the year 2021, astronomers are still unsure if its orbit is perfectly circular or slightly elongated, but they believe the planet has little to no tilt in its rotation. The age of Proxima Centauri b is unknown. Interestingly, Proxima Centauri itself may have been captured by the Alpha Centauri system at some point in the past, which means it might not be the same age as the other two stars, Alpha Centauri A and Alpha Centauri b, both of which are about 5 billion years old. Because of its proximity to its star, Proxima Centauri b is very unlikely to have stable moons. By the year 2025, astronomers estimated the minimum mass of Proxima Centauri b to be about 1.055 Earth masses, with a margin of error of about 0.055. If the orbit is tilted at about 47 degrees to our line of sight, then the true mass would be closer to 1.44 Earth masses. That makes it very similar to Earth in size, but the exact radius of the planet remains uncertain. Depending on its composition, it could be slightly smaller than Earth or up to 40% larger. Some models suggest it could be like Mercury, with a large metal core, while others imagine it as a water-rich world. Measurements of the star's elemental makeup, particularly iron, silicon and magnesium, may eventually help scientists determine the likely composition of the planet. Although little is directly known, computer simulations have been used to explore possible properties of Proxima Centauri b. These models consider Earth-like geology, internal heating from radioactive decay, tidal heating from the star, magnetic fields, possible amounts of water or other volatile substances, and how all of these factors might change over billions of years. Most scientists think the planet did not form where it is today. Instead, it probably developed farther away from the star, where more material was available, and later migrated inward to its current close orbit. This migration would have greatly influenced its makeup. Depending on the materials involved, Proxima Centauri b could have ended up with a very dry surface, like Mercury, or with abundant water and ices. Different formation scenarios remain possible, many of which depend on whether other planets are present in the Proxima system. Scientists believe that Proxima Centauri b, the planet orbiting the small red star Proxima Centauri, may be tidally locked to its star. This means that, just like our moon always shows the same face to Earth, Proxima Centauri b might always keep one side facing its star. If that were the case, one side of the planet would be in endless daylight, while the other side would be locked in permanent darkness. Such a situation would create very harsh conditions, with only certain regions between the hot side and the frozen side possibly able to support life. But researchers also point out that the planet might not actually be tidally locked. If the shape of its orbit is slightly stretched instead of perfectly circular, that is, if its orbital eccentricity is greater than about 1/10, or even as low as 6/100ths, then the planet could enter into a different rhythm, something like the planet Mercury in our solar system. Mercury spins 3 times on its axis for every 2 orbits around the Sun. In a similar way, Proxima Centauri b might spin in a 3:2 resonance, or perhaps even follow other ratios such as 2:1. Interactions with other possible planets around Proxima Centauri, or even gravitational nudges from the nearby Alpha Centauri star system, could also increase its orbital eccentricity. If the planet is not a perfectly round sphere but instead has an uneven, stretched shape, then it could be captured into one of these non-locked spin states even with very little eccentricity. However, being in a non-locked orbit comes with its own challenges. The constant stretching and squeezing of the planet by tidal forces would heat up its rocky interior, creating volcanic activity and possibly interfering with the dynamo effect that could generate a protective magnetic field. How exactly this works depends heavily on the inner structure of the planet and how it responds to this tidal heating over time. Now, let us look at the parent star itself, Proxima Centauri. This star is a red dwarf, which means it is a small, dim star that burns hydrogen very slowly compared to our Sun. Proxima Centauri shines with only about 0.005% of the visible light that our Sun gives off, and on average it produces about 1/6 of the Sun's total energy output. Despite being such a weak star, Proxima Centauri b orbits very close to it, so it still receives around 70% of the infrared radiation that Earth gets from the Sun. But there is a catch. Proxima Centauri is what astronomers call a flare star. At times it can suddenly brighten 100-fold within only a few hours. Its overall average brightness is measured at about 15.5% of the Sun's light output. In terms of size and mass, Proxima Centauri has only about 12.2% of the Sun's mass and about 15.4% of the Sun's radius. Its surface temperature is about 3050 Kelvin, which is much cooler than the Sun's roughly 6000 Kelvin. Proxima Centauri belongs to the spectral class M, more precisely an M5.5v type, meaning it is still on the main sequence of stars, steadily fusing hydrogen at its core. Its magnetic field is also far stronger than the Sun's, reaching an intensity of about 600 Gauss, and it cycles in strength roughly every 7 years. This star is the closest star to our Sun, which is why it is named Proxima, meaning nearest. It lies about 4.24 light-years away, which is roughly 1.3 parsecs. Proxima Centauri is part of a 3-star family, along with Alpha Centauri A and Alpha Centauri B, which orbit each other as a close binary pair. Over billions of years, the gravitational pull from these stars may have changed Proxima Centauri B's orbit, drawing it closer to its star. In the year 2012, astronomers thought they had discovered a planet around Alpha Centauri itself, but this finding later turned out to be uncertain. Despite being so close to Earth compared to other stars, Proxima Centauri is too faint to be seen without a telescope, except perhaps during one of its extremely powerful superflares. Proxima Centauri b lies in what astronomers call the classical habitable zone, the region around a star where liquid water could exist on the surface. The planet receives about 65% of the energy Earth gets from the Sun. Its estimated average surface temperature is about 234 Kelvin, which is roughly 39 degrees below 0 Celsius, or 38 degrees below 0 Fahrenheit. Whether this planet could actually support life depends on many factors: the details of its orbit, the kind of light its star produces, and the behaviour of any clouds or hazes that might form in its atmosphere. There are two main possibilities for what kind of atmosphere Proxima Centauri b might have. One idea is that in its early history its water condensed while its lighter hydrogen gas escaped into space, leaving behind an atmosphere rich in oxygen or carbon dioxide. Another possibility is that the planet originally formed farther from its star and later moved inward, keeping much of its water and perhaps even some hydrogen. If Proxima Centauri b does have an atmosphere, it would likely contain gases like oxygen and carbon dioxide. Combined with the star's strong magnetic activity, these gases could create colourful auroras in the planet's skies, perhaps even visible from Earth with powerful telescopes, but only if the planet has its own magnetic field. Scientists have used advanced climate models, the same kind used to study Earth's weather and long-term climate, to explore what conditions might exist on Proxima Centauri b. The results suggest many possible worlds. The planet could be completely frozen over, partly covered in ice, or it could have small or large oceans. It might even host a strange landscape with eyeball Earth patterns, where one side facing the star has a central ocean surrounded by ice, while the rest of the planet remains frozen. Another possibility is a lobster-shaped region of liquid water near the equator, with two branching areas of open ocean stretching out like claws. Some researchers also suggest that beneath a kilometre-thick shell of ice, Proxima Centauri b could hide a slushy global subsurface ocean. A huge number of other factors would influence its climate: the way heat moves through its atmosphere by convection, the presence of continents, which could help regulate carbon dioxide through the carbonate-silicate cycle, the bombardment of cosmic rays, which would be stronger here than on Earth, the circulation of heat by oceans, which could spread warmth across the planet, the salinity of those oceans, which would change how they behave, ozone chemistry, which could raise temperatures in the upper atmosphere and affect the surface, the speed at which the planet rotates, which controls the formation of atmospheric waves, the flow of internal heat, which could melt ice sheets from below, the dynamics of sea ice, which could either trap the planet in a global freeze or keep areas of ocean open. One of the biggest questions about whether life could exist on Proxima Centauri b is whether the planet can even keep an atmosphere. The stability of its atmosphere is uncertain, and many factors that affect it are still unknown. To begin with, Proxima Centauri is a red dwarf star that bombards its planet with huge amounts of high-energy radiation, particularly ultraviolet light and powerful X-rays. Proxima Centauri b receives between 10 and 60 times more of this harsh radiation than Earth does, especially in the form of X-rays. Scientists believe that in the distant past the planet may have been blasted with even more radiation, perhaps around 7 to 16 times more cumulative, extreme ultraviolet and X-ray energy than Earth has ever received. This kind of radiation is dangerous to a planet's atmosphere. Hydrogen, which is the lightest of all gases, is very good at absorbing this energy. Once heated, hydrogen atoms and molecules can move so fast that they escape the planet's gravity and drift into space. In the process, the radiation can also split water molecules into hydrogen and oxygen, with the hydrogen escaping while dragging oxygen and even nitrogen along with it. Over time, this means a planet can lose much of its water and atmosphere. Heavier gases like nitrogen and carbon dioxide can sometimes leak away on their own too, though this process is generally slower and would not completely strip away an Earth-like atmosphere. But radiation is only one danger. Stellar winds and violent bursts of plasma called coronal mass ejections pose an even greater threat. The stellar wind from Proxima Centauri is thought to hit Proxima Centauri b with a force that could be between 4 and 80 times stronger than the solar wind that strikes Earth. Even more alarming, the pressure of this wind may be about 10,000 times greater than the solar wind produced by our Sun. The strong ultraviolet and X-ray radiation can puff up the upper atmosphere of the planet so much that it extends beyond its protective magnetic field, making it easier for the stellar wind to strip the gases away. Another complication is the magnetic cycle of Proxima Centauri itself. Unlike the Sun, which has an 11-year cycle, Proxima Centauri has a 7-year-long magnetic cycle. Depending on which stage of this cycle the star is in, the stellar wind near Proxima Centauri b may be 10 to as much as 1,000 times denser than what Earth experiences. As of the year 2018, scientists still do not know whether Proxima Centauri b even has a global magnetic field at all. It is possible that only the upper layers of its atmosphere generate a magnetic field. If the planet does not have a strong internal magnetic field, the stellar wind could push deep into the atmosphere and peel away parts of it, a process that might vary greatly from day to day, or even from year to year. There is also the issue of tidal locking. Because the planet is so close to its star, it may always keep the same side facing Proxima Centauri, much like the Moon always shows the same face to Earth. If that is the case, the side facing away from the star could become so cold that the atmosphere might freeze and collapse there, especially if it is made mostly of carbon dioxide. In such a situation, frozen carbon dioxide could collect into glaciers, which might recycle and spread again, but this would still be a major challenge for habitability. Another factor has to do with the history of the star itself. Unlike stars like our Sun, red dwarfs such as Proxima Centauri used to shine even more fiercely during their early years, when they were still in the so-called pre-main sequence stage. Back then, the habitable zone, the region around the star where liquid water can exist, was farther away than it is now. This means that if Proxima Centauri b formed in its current orbit, it may have spent as much as 180 million years, much too close to its star for water to ever condense. During that time, the planet might have gone through a runaway greenhouse effect, with its water boiling into steam, being broken apart by ultraviolet light, and losing its hydrogen into space. This is a fate similar to what scientists believe happened to the planet Venus in our own solar system. Adding to all this, violent asteroid impacts could also destabilize Proxima Centauri b's atmosphere, or even boil away any oceans that might exist there. On the other hand, there are also possible ways for the planet to recover. If Proxima Centauri b were covered in ice with an ocean hidden beneath, it might experience cryovolcanism, eruptions of water and ice instead of molten rock, at levels comparable to the volcanic activity on Io, one of Jupiter's moons. This process could generate a thin exosphere, like the faint atmosphere found on Jupiter's moon Europa. Even if Proxima Centauri b lost its first atmosphere long ago, volcanic activity could eventually rebuild a second one. Such a new atmosphere would likely contain large amounts of carbon dioxide, which is heavier and more stable than a nitrogen-rich Earth-like atmosphere. If oceans are present, they could help balance and stabilize this second atmosphere, preventing it from collapsing. Additionally, if comets exist in the Proxima Centauri system, their icy impacts could deliver fresh water to the planet over time, helping to restore what was lost. Scientists believe that a young planet like Proxima Centauri b could receive water in several different ways. Water might arrive through icy comets crashing into the planet, or through chemical reactions in the early atmosphere and surface. Yet, no one knows exactly how much water Proxima Centauri b actually gained during its formation. A study by Rebus and his team in the year 2016 suggested that the planet may have lost no more than the equivalent of one entire Earth ocean's worth of water. Later studies, however, pointed to the possibility that the losses could have been far greater. In fact, in the year 2017, Erepetian and colleagues argued that the planet might lose its whole atmosphere in less than 10 million years. These predictions, though, depend heavily on how massive the atmosphere was to begin with, something that remains very uncertain. When astronomers talk about the habitability of a world, they usually mean one simple thing: can liquid water exist on the surface? For most definitions of life beyond Earth, liquid water and a protective atmosphere are essential. Of course, it is possible that life could hide below the surface, in underground oceans like the one suspected beneath the icy shell of Europa, one of Jupiter's moons in our solar system. But life like this would be very hard to detect from light years away. Even so, scientists sometimes imagine Proxima Centauri b as a frozen, ocean-covered world that might shelter hidden seas beneath its surface. The habitability of planets around red dwarfs, like Proxima Centauri, is one of the most hotly debated topics in astronomy. Several challenges stand in the way. Proxima Centauri itself is a very active star. Its flares and bursts of radiation, combined with the effect of tidal locking, which keeps one side of the planet always facing the star, could make it very hard for stable, life-friendly conditions to form. Unlike the harsher X-ray and extreme ultraviolet radiation, Proxima Centauri's ultraviolet light is somewhat redder and cooler. This means it interacts less strongly with organic molecules and might create less protective ozone. Yet, ironically, the star's violent outburst could strip away any ozone layer that does form, leaving the surface exposed to dangerous radiation. If the planet's orbit is not perfectly circular, it might drift in and out of the habitable zone during its journey around the star, further complicating the chance of stable conditions. Certain gases such as oxygen and carbon monoxide might build up in the atmosphere to toxic levels. On the other hand, high oxygen could also make the rise of complex life more likely. If oceans exist, tides caused by the pull of the star could shape the environment. Coastlines might experience cycles of flooding and drying, sparking chemical reactions that could help life get started. Tides might also encourage the rise of natural biological rhythms, similar to Earth's day and night cycles, and stir the oceans to mix nutrients, fueling the growth of marine organisms. Red dwarfs do have one advantage, however. They live far longer than stars like our Sun, outlasting even the current age of the universe. That means they could give life plenty of time to evolve. But their light is not well suited for Earth-like photosynthesis that produces oxygen. Instead, it might only allow anoxygenic photosynthesis, a different process that does not release oxygen. Whether such life could be recognised from Earth remains a mystery. One study in the year 2017 even estimated that the productivity of an ecosystem on Proxima Centauri b might be only about 1/5 of what Earth's ecosystems achieve. As of the year 2021, no telescope has been able to directly take an image of Proxima Centauri b. The planet orbits too close to its star, and from Earth's point of view it does not seem to pass in front of the star. Careful searches for such transits have all come up empty. Still, scientists are listening closely. In April and May of the year 2019, the Breakthrough Listen project detected a strange signal called BLC-1 that seemed to come from Proxima Centauri's direction. Hopes briefly rose that it might be a sign of alien technology, but later studies showed it was almost certainly a signal created by humans on Earth. Future instruments, however, may change everything. Giant ground-based telescopes and powerful space observatories, like the James Webb Space Telescope and the Nancy Grace Roman Space Telescope, may one day separate the light of Proxima Centauri b from its star. If so, astronomers could study whether the planet reflects starlight from an ocean, examine the fingerprints of gases in its atmosphere, and even look at how heat moves across its surface. Reaching Proxima Centauri b in person is another story. Even Voyager 2, one of the fastest spacecraft ever built by humans, would need about 75,000 years to get there. New ideas like ultra-thin solar sails that travel at 1/5 the speed of light have been suggested, but such spacecraft would face challenges, such as slowing down when they arrive, or surviving impacts with tiny particles in interstellar space. One ambitious program, the Breakthrough Starshot project, aims to make this dream possible within the 21st century. If you were standing on Proxima Centauri b and looked up at the sky, the view would be breathtaking. The two bright stars of the Alpha Centauri pair would shine far more brilliantly than Venus does in our skies, with dazzling magnitudes of -6.8 and -5.2. The Sun itself would appear as a modest star in the constellation of Cassiopeia, with a brightness similar to stars like Achernar or Procyon. The familiar constellations would look familiar yet strange, with Sirius glowing near Betelgeuse, Procyon sparkling in Gemini, and our Sun shining faintly between Perseus and Cassiopeia. From Earth, astronomers know where to look. In the southern constellation of Centaurus, on clear dark nights, they can point their telescopes toward the faint red glow of Proxima Centauri, the closest star to our solar system, hidden just beyond the reach of the naked eye. PSRB 162026b is an extraordinary exoplanet located roughly 12,400 light-years away from Earth in the constellation of Scorpius. Astronomers often call it by two remarkable nicknames, Methuselah and the Genesis planet. These names are inspired by the biblical figure Methuselah, who is said to be the oldest person to have ever lived. The names fit perfectly, because this planet itself is unimaginably ancient. What makes this world even more special is that it orbits not just one star, but two stars at the same time. This type of path is called a circumbinary orbit. The two stars in question are very unusual. One is a pulsar, known as PSRB 162026a, which is a dense spinning neutron star, and the other is a white dwarf, known as WDB 162026. This was the very first circumbinary planet ever confirmed, and it was also the first planet ever found inside a globular cluster. To this day, it remains one of the oldest known planets in the universe, with an age estimated to be around 12.7 billion years. That is nearly 3 times as old as Earth. PSRB 162026b is a giant world, with a mass about 2.5 times greater than that of Jupiter. It circles its stars at a distance of about 23 astronomical units, which is more than 3 billion kilometres away, a little farther out than Uranus is from the Sun. Because it is so far from its stars, each orbit takes roughly 100 Earth years to complete. This entire system lies just outside the crowded heart of the globular cluster Messier 4. Since all the stars inside a globular cluster form at nearly the same time, and since planets are born alongside their host stars, astronomers are confident that PSR B162026b is also about 12.7 billion years old. By comparison, our Sun is only about 4.6 billion years old, making this planet truly ancient in cosmic terms. The pulsar itself is astonishing. It spins at an incredible speed of about 100 times every single second. Despite its small size, likely only around 20 kilometres across, it holds more mass than our entire Sun, about 1.3 times the Sun's mass. Its surface temperature is thought to be as high as 300,000 Kelvin. The white dwarf companion is far smaller, with a mass only about 1/3 that of the Sun, and a radius of about 1% of the Sun's size. Its surface temperature is estimated at around 25,200 Kelvin. These two stars circle each other at a distance of about 1 astronomical unit, completing their mutual orbit roughly every 6 months. With an age of between 12.7 and 13 billion years, this pair ranks among the oldest known binary star systems. From Earth's perspective, the brightness of this binary system is faint indeed. Its apparent magnitude is 24, making it far too dim to be seen without powerful telescopes. The origin of PSRB 162026b is still a mystery. It is unlikely that the planet formed around the pulsar after its violent birth, because when a massive star collapses into a neutron star, it explodes as a supernova and loses most of its mass, a process that usually destroys or ejects nearby planets. Instead, scientists believe the planet was originally formed around the star that is now the white dwarf, and later this star, along with its planet, was captured into orbit around the pulsar during a close encounter in the crowded cluster. In our part of the Milky Way galaxy, such close stellar encounters are rare, but in dense globular clusters like Messier 4, they are fairly common. Astronomers think that around 10 billion years ago, the neutron star captured the white dwarf's predecessor star, while likely losing another star it had been orbiting with. Roughly 500 million years ago, that captured star began to swell into a red giant as part of its natural evolution. As this happened, it began pouring gas and outer layers of matter onto the pulsar. This dramatic process spun the pulsar up to its current dizzying speed of just a few milliseconds per rotation. For several 100 million years, the system blazed as a low-mass X-ray binary, as the infalling matter grew so hot that it glowed with high-energy X-rays. Eventually, the red giant used up its outer layers and shrank into the white dwarf we see today. Now the two stars orbit each other calmly, with the planets circling both of them from afar. But the future of PSR B162026b is not secure. The entire triple system is slowly drifting toward the dense central region of Messier 4. In another billion years or so, it will likely pass close to another star. When that happens, the lightest member of the system, the planet itself, is expected to be ejected. If so, PSR B162026b will be cast adrift, leaving its cluster behind to wander endlessly through interstellar space as a lonely, orphaned planet. Like many of the planets discovered outside our solar system before the year 2008, the planet known as PSR B1620-26b was first found through a clever method that astronomers often use when they cannot see a planet directly. Instead of spotting the planet itself, they look for tiny shifts in the light or radiation coming from the star that the planet orbits. These shifts, called Doppler shifts, are caused by the gravitational tug of the planet as it circles its star. In this special case, the star in question was actually a pulsar, a kind of dead star that spins rapidly and sends out beams of radiation, like a cosmic lighthouse. Astronomers noticed that the pulses from the pulsar seemed to change in rhythm, as though something was pulling on it. In the early 1990s, a group of astronomers led by Donald Backer was studying what they thought was a pair of stars locked together in orbit, a so-called binary pulsar. But soon, their careful measurements told them something surprising. Two objects alone could not explain the strange shifts they were seeing. A third object had to be there, tugging gently but unmistakably on the pulsar. Within just a few years, they were able to measure the gravitational effects of this hidden companion on the orbit of both the pulsar and its nearby white dwarf star. The measurements showed that this mysterious object was far too small to be another star. The only explanation was that it was a planet. In the year 1993, Stephen Thorset and his collaborators made the exciting announcement that the third object was indeed a planet. Studying the way the planet moved also allowed scientists to learn more about the white dwarf star that shared the system. They could estimate its mass, and, based on theories of how such a planet might have formed, they suspected that the white dwarf should be relatively young and still very hot. On the 10th of July in the year 2003, a team of astronomers led by Stein Sigurdsson used the powerful Hubble Space Telescope to finally detect the white dwarf directly. Their findings confirmed the predictions. At a NASA press conference announcing the discovery, the planet was given the nickname Methuselah, after the biblical figure who was said to have lived longer than anyone else. This dramatic name captured the imagination of the press and quickly spread around the world. In scientific circles, the planet is officially listed in the Simbad Astronomical Database as PSR B1620-26b. However, some popular sources have occasionally called it PSR B1620-26c, since it is technically the third member of its unusual triple system, the pulsar, the white dwarf, and the planet. But this label does not appear in official records, and it does not follow the modern rules for naming. Astronomers today use a system where stars are given uppercase letters and their planets lowercase letters. For example, Gliese 667cc means the C planet orbiting the star Gliese 667c, which itself is the third star in a triple star system. By this rule, the correct designation for the planet is PSR B1620-26b, since it orbits both the pulsar and the white dwarf. Still, outside scientific journals, people continue to call the planet Methuselah. This informal name makes it feel more like the planets in our own solar system, which all carry mythological or historical names. In fact, Methuselah is the only planet known outside our solar system that has ever been given a biblical nickname. A few others, however, have received unofficial mythological or personal nicknames. For example, the planet called Dimidium, which was once nicknamed Bellerophon, the debated world Gliese 581g, sometimes called Zomina, or Zomina's world, after the wife of one of its discoverers, and the planet HD 209458b, which has occasionally been called Osiris. Thus, Methuselah remains a fascinating world, not just because of its unusual discovery and its strange home among a pulsar and a white dwarf, but also because of the powerful name it carries, a name that links the cold emptiness of deep space to one of humanity's oldest stories. Coro T7b, which was first called Coro TXO7b, is an exoplanet that circles around the star Coro T7, in the constellation known as Monoceros, the Unicorn. It lies about 489 light-years away from Earth, which is the same as about 150 parsecs. The planet was first detected through light observations by the French-led Coro T mission, and its discovery was officially reported in February of the year 2009. At that time, Coro T7b held a very special record, until January of the year 2011, when Kepler 10b was announced. Coro T7b was the smallest exoplanet ever to have its diameter measured. It was measured at about 1.58 times larger than Earth's diameter, which makes its overall volume about 3.95 times that of Earth. It also carried the honour of being the very first rocky Earth-like planet found outside our solar system, rather than a gas giant like Jupiter. One of the most unusual things about Coro T7b is its extremely short orbit. It circles its star in only about 20 hours, meaning that a year on Coro T7b lasts less than one single Earth day. By combining data from two methods, the planet's diameter from its transit across the star and its mass from radial velocity measurements, scientists discovered that the planet's density is about the same as Earth's. This means that Coro T7b is indeed a rocky world, not a giant ball of gas. During these same observations, astronomers also found another planet in the system, named Coro T7c. This second world is a super-Earth, with a mass about 8.4 times greater than Earth's. It orbits its star once every 3.7 days at a distance of about 6.9 million kilometres, which is equal to about 0.046 astronomical units, or roughly 4.3 million miles. Coro T7b was discovered by watching its star for tiny dips in brightness. Each time the planet passed in front of the star from our point of view on Earth, the star's light dimmed slightly. By measuring how much the light dipped and knowing the star's size, astronomers were able to calculate the size of the planet. The Coro T spacecraft studied the star between October 15th of the year 2007 and March 3rd of the year 2008 in the observing field known as ELRA-01. During this time, the spacecraft recorded 153 transit signals, each lasting about 1.3 hours, with a brightness drop of about 3.4 times 10 to the power of -4. After about 40 days of data collection, the spacecraft's alarm mode detected the signal of Coro T7b, which then triggered more ground-based observations to confirm that the object was truly a planet. The official announcement of Coro T7b came a year later, on February 3rd of the year 2009, at the Coro T Symposium held in Paris. The discovery was then published in a special issue of the journal Astronomy and Astrophysics, which was devoted to results from the Coro T mission. Follow-up observations with telescopes on Earth ruled out almost all chances that the signal was a false detection. Later, the HARP spectrograph was used to measure the planet's mass using the radial velocity method. However, the star itself is very active, which disturbed the measurements and made finding the true mass of the planet very difficult. The first published study by Queloz and colleagues estimated the planet's mass to be about 4.8 times that of Earth. This gave it a density of about 5.6 grams per cubic centimetre, with an uncertainty of plus or minus 1.3, which is very close to Earth's own density. The study also suggested that there was a second planet in the system, Coro T7c, with a 3.7-day orbit. Another study by Hatzis and colleagues, which used Fourier analysis, suggested that Coro T7b might actually be heavier, with a mass closer to 6.9 times Earth's. They also found possible evidence for a third planet, Coro T7d, with a mass similar to Neptune's and an orbital period of about 9 days. Other researchers pointed out possible problems in the data. Pont and colleagues argued that there were larger errors in the HARP's measurements than first thought, and estimated that Coro T7b's true mass might lie anywhere between 1 and 4 times Earth's. They also said that the radial velocity confirmation of the planet was on shaky ground, with only about 1.2 sigma certainty. Later, Boisset and colleagues tried to separate the signals caused by the star's activity from those caused by the planet. Their results suggested a mass of about 5.7 Earth masses, but with very large uncertainty. The Coro T team then published a second paper, analysing only those datasets where several measurements were taken on the same night to minimise stellar noise. From this method, they estimated a higher mass of about 7.42 Earth masses, which meant an average density of 10.4 grams per cubic centimetre, much denser than Earth and closer to the rocky planet Kepler-10b. Finally, Farasmello and colleagues used an improved method and found that earlier studies had underestimated the signals. Their result gave CoROT-7b a mass of about 8 Earth masses, supporting the idea that it is a rocky planet with a huge iron core, more similar in structure to Mercury than Earth. An independent check came from NASA's Spitzer space telescope. Spitzer confirmed that CoROT-7b truly transits its star, with the same depth of dimming seen at different wavelengths of light. This confirmation, independent from the noisy radial velocity data, gave scientists very high confidence that CoROT-7b is indeed a genuine planet. Its exact mass is still somewhat uncertain, but scientists estimate it to be a little over 6 times the mass of Earth, with a margin of error of about 2/3 of an Earth mass. However, its size and orbit are much better understood thanks to careful observations from the CoROT space telescope. This planet races extremely close to its parent star. So close, in fact, that the distance is only 1/23 of the gap between the Sun and tiny Mercury. Because of this extreme closeness, it completes one full trip around its star in just 20 hours, 29 minutes, and a little over 9 seconds. Its radius is measured to be about 1.5 times that of Earth. At the time it was discovered, CoROT-7b held the record for having the shortest orbital period of any known planet. Living under such intense conditions, the surface of CoROT-7b is believed to be unimaginably hot, possibly covered by vast seas of glowing lava. The composition and density of the planet, though not perfectly pinned down, suggest that it is rocky, much like Earth. Some scientists have wondered if it could belong to a special group of planets that contain not only rock, but also a large amount of water, perhaps as much as 40% of their mass. Yet, because this planet formed so close to its fiery star, it is more likely that most of its water and other volatile materials boiled away long ago. It is very likely that CoROT-7b's rotation has become tidally locked, meaning one side of the planet is forever turned toward the star while the other remains in eternal darkness. This would create extreme differences between the blazing day side and the frozen night side. Some theories even suggest that CoROT-7b might be what astronomers call a Chthonian planet, the leftover core of a gas giant like Neptune, stripped of its thick atmosphere by the star's powerful radiation. Others disagree, pointing out that the system is relatively young, making it more likely that CoROT-7b has always been a rocky planet. If its orbit is not perfectly circular, the gravitational tug from its star and from nearby planets could twist and stretch it, creating intense volcanic activity similar to the eruptions seen on Jupiter's moon Io. Detailed studies of CoROT-7b have revealed just how extreme this planet truly is. Even with uncertainties in its exact mass, it appears Earth-like in composition, though far too close to its star to hold onto a thick atmosphere. On its permanent day side, temperatures may rise as high as the filament of a glowing light bulb, hot enough to melt rock into oceans of lava. Because of this, scientists have suggested that CoROT-7b could be the first known example of a new category of exoplanets, which they call lava ocean planets. Models suggest that if the planet has about 5 times the mass of Earth, its internal structure would include a mantle with circulating rock currents and a small iron core no more than 15% of the planet's mass, that is, less than 1 Earth mass. The mantle near the surface would move more actively than the deeper layers, since greater pressure below makes the rock more sluggish and sticky. On the searing day side, where the planet's face is scorched by continuous starlight, the crust itself likely melts and becomes part of the convective currents, forming a vast molten sea. On the freezing night side, a crust forms, though still riddled with volcanic pools of lava bubbling up from beneath. Interestingly, the convection cells on the hot day side are thought to be larger than those on the cooler night side. Researchers also believe that CoROT-7b probably has a solid iron core, but because of its structure, it is unlikely to generate its own magnetic field. The extreme heat on the star-facing side of the planet means that most of its lighter substances have boiled away. Instead, its thin atmosphere is thought to be made of rock vapour. At a temperature of around 2,500 kelvins, that is, about 2,230 degrees Celsius, or 4,040 degrees Fahrenheit, the pressure may reach only 1 Pascal, far thinner than Earth's atmosphere. This vapour may contain sodium, oxygen, silicon monoxide, and small amounts of potassium and other metals. Minerals such as statite, corundum, spinel, wollastonite, silica, and iron oxide might condense out of this vapour and fall like strange mineral rain onto the surface. Elements such as titanium and iron may drift to the cooler night side before condensing into minerals like perovskite and geekylite. Meanwhile, sodium, being more volatile, would stay aloft longer and dominate the thin atmosphere. Yet, when astronomers looked closely using highly sensitive instruments to detect traces of sodium or calcium in the planet's outer layers, they found nothing. Even signs of volcanic gases expected from tidal heating were missing. This matches the idea that Corot 7b's atmosphere is not like that of Mercury or any planet we know, but instead is a cloudless, ghost-thin shroud of rocky vapours. From all the evidence gathered so far, scientists conclude that Corot 7b is unlike any of the rocky planets in our solar system. It is an alien world, a blazing inferno of stone and fire forever locked in a struggle with the star it circles so tightly. HD 189 733b is a fascinating exoplanet located in the small constellation known as Vulpecula, which means the little fox. It lies about 64.5 light-years away from our solar system, or nearly 20 parsecs in astronomical measurement. This distance makes it one of the closest hot Jupiters known to astronomers. The planet was first discovered on the 5th day of October, in the year 2005, by a group of French astronomers. They spotted it by watching how the planet passed in front of its star, temporarily dimming the star's light, an event known as a transit. Later, it was also confirmed through a technique called Doppler spectroscopy, which measures the tiny wobbles in a star's motion caused by the gravitational tug of an orbiting planet. HD 189-7. 33b is a giant world, slightly bigger and heavier than Jupiter, the largest planet in our solar system. Its mass is about 16% greater than that of Jupiter, and its radius is about 11% larger. The planet races around its host star at an extraordinary speed, more than 152 kilometers per second, which equals roughly 341,000 miles per hour. At that pace, it completes a full orbit in just a little more than 2 days. Because it circles so close to its star, the planet is scorched and inhospitable, falling into the category astronomers call a hot Jupiter. Despite its harsh nature, HD 189 733b has become one of the most studied exoplanets in history. It was the very first exoplanet to have a thermal map of its surface created, showing temperature differences between its day and night sides. It was also the first to have its colour determined, a striking cobalt blue, most likely caused by Rayleigh scattering in its atmosphere, the same effect that makes Earth's sky appear blue. Scientists have also observed it in X-ray light, confirmed the presence of carbon dioxide in its skies, and even found signs of wild weather, including winds so fierce that they may drive molten glass rain sideways across the planet. On the 6th day of October in the year 2005, another team of astronomers publicly announced their independent detection of HD 189 733b. Then, in the year 2006, a group led by Drake Deming discovered strong thermal emissions in the infrared, measured during a secondary eclipse, when the planet slips behind its star and its heat is briefly blocked from view. NASA's Spitzer Space Telescope later joined the effort. On the 21st day of February in the year 2007, NASA revealed that Spitzer had collected detailed spectra from HD 189 733b and another hot Jupiter, HD 209,458b. These observations helped researchers understand the chemical composition and heat distribution in the planet's atmosphere. In the year 2008, scientists attempted to detect the planet's reflected light using a technique called polarimetry. This would have been the first time visible light was directly observed from an exoplanet. By the year 2011, the same team refined their measurements and suggested that the planet reflects more blue light than red, again pointing toward Rayleigh scattering. In the year 2013, the planet's deep blue colour was confirmed by yet another technique, making HD 189 733b the first world whose colour had been determined through 2 separate methods. However, later studies using more advanced polarimeters questioned these results, placing stricter limits on how much light the planet actually reflects. In January of the year 2008, astronomers carried out detailed spectral observations during a transit of the planet. These revealed important details about its atmosphere. If molecular hydrogen is present, it corresponds to a pressure of about 410 millibars, with some uncertainty of plus or minus 30 millibars. Models also suggest that tiny particles of magnesium silicate, the same mineral found in Earth's rocks, may form hazes or clouds in its skies. The temperatures are extreme, ranging between about 1340 and 1540 kelvins, hotter than molten lava on Earth. In the visible spectrum, astronomers have also detected elements such as sodium and potassium, using powerful instruments like the UV spectrograph on the European Southern Observatory's Very Large Telescope in Chile. These studies not only confirm the composition of the atmosphere, but also provide hints about its temperature and pressure. More recently, in the year 2024, scientists used the high-precision espresso spectrograph to refine our knowledge of HD 189 733b's atmosphere. They confirmed the presence of sodium and, for the very first time, detected lithium in its skies. They also noticed that the sodium signals were shifted in wavelength, a sign of fast and powerful winds sweeping through the atmosphere. However, these measurements also revealed a challenge. The signals from the planet are often distorted by the star itself, due to its rotation, surface activity, and limb darkening. This phenomenon, called planet-occulted line distortion, shows just how complex and delicate the task of studying exoplanet atmospheres really is. Together, all of these discoveries make HD 189 733b one of the most remarkable exoplanets ever observed. Its close distance to Earth, blazing speed, dazzling blue colour, and stormy atmosphere have made it a true laboratory for understanding the strange and exotic worlds that exist beyond our solar system. In the month of July, in the year 2013, NASA announced something remarkable. For the very first time, astronomers had observed a planet passing in front of its star while being studied in the X-ray spectrum. What they found was surprising. This planet's thick atmosphere blocks about 3 times as many X-rays as it does visible light. Earlier, in the month of March in the year 2010, other observations using a special ultraviolet wavelength known as hydrogen Lyman alpha showed that the planet is actually evaporating into space. Its atmosphere is being stripped away at an enormous rate, somewhere between 1 and 100 gigagrams of gas every second. Scientists discovered this because they detected a huge extended cloud of hydrogen atoms, called an exosphere, surrounding the planet. This made HD 189 733b only the second planet ever found, after HD 20958b, to show clear signs of its atmosphere escaping into space. This alien world is also known for producing one of the deepest transits ever measured in astronomy. When it crosses in front of its parent star, it blocks about 3% of the star's light, a very large amount for an exoplanet. The tilt of its orbit, known as the longitude of the ascending node, lies about 16 degrees away from the north-south direction in our sky, with a possible error of about 8 degrees. Alongside HD 20958b, it was among the first 2 planets to be studied directly using spectroscopy, a technique that allows scientists to break apart the light and see what gases make up the atmosphere. Both planets orbit stars that are very bright compared to other exoplanet host stars, which is why they continue to draw so much attention from astronomers. Like most planets of its kind, so-called hot Jupiters, HD 189 733b is believed to be tidally locked. This means that one side of the planet always faces its star in eternal daylight, while the other side remains in everlasting night. Interestingly, the planet is not squashed or oblate in shape, nor does it have large moons bigger than about 80% of Earth's radius. It also lacks the spectacular ring system we see around Saturn. An international team led by Svetlana Berdugina of the Zurich University of Technology, using the 60-centimetre Swedish KVA telescope in Spain, managed to detect the faint glow of polarized light reflecting off the planet. This showed that the scattering atmosphere of HD 189 733b is at least 30% larger than the solid opaque body of the planet itself. At first, scientists thought the planet's atmosphere belonged to what they called the PL class, meaning it did not have a temperature inversion layer in its stratosphere. This would make it somewhat similar to very cool brown dwarfs, which also lack certain chemicals like titanium and vanadium oxides. Later observations tested this theory, but the results were inconclusive. However, scientists did discover that high in the atmosphere, about 1,000 kilometers above the main body, there is a hazy layer that makes the sky look red when viewed during sunset. Early predictions also suggested that the atmosphere should contain traces of sodium and potassium. At first, these were hidden behind the haze, but sodium was eventually detected at 3 times the concentration of the sodium layer found in HD 20,958b. Potassium was detected much later, in the year 2020, although it was present only in small amounts. HD 189 733b was also the first extrasolar planet where astronomers confirmed the presence of carbon dioxide in its atmosphere. Even more recently, in the year 2024, hydrogen sulfide, a gas that smells strongly of rotten eggs, was also found in the planet's skies. Back in the year 2007, the Spitzer Space Telescope was used to carefully measure the planet's heat. Over the course of 33 hours, astronomers watched the world complete half of its orbit. They discovered that temperatures range between about 973 kelvins, roughly 700 degrees Celsius, and 1212 kelvins, close to 940 degrees Celsius. This revealed that the planet's atmosphere distributes heat fairly evenly across its surface, although the hottest region was shifted about 30 degrees east of the point directly facing the star. This fit predictions from models of hot Jupiters, which suggest strong winds move heat from the day side to the night side. Indeed, scientists at the University of Warwick later determined that winds on this planet reach astonishing speeds, up to 8,700 kilometers per hour, or 5,400 miles per hour, making them some of the fastest winds ever recorded on any world. NASA even published the first ever brightness map of an exoplanet based on these temperature readings. On the 11th of July in the year 2007, a team led by Giovanna Tinetti announced that they had detected strong evidence of water vapour in the atmosphere of HD 189 733b. This discovery was later confirmed by the Hubble Space Telescope, which also found neutral oxygen and methane, an organic compound. Later still, the Very Large Telescope in Chile detected carbon monoxide on the planet's dayside. The discovery of methane was especially puzzling, since the extreme heat of the atmosphere, about 700 degrees Celsius, should normally cause methane and water to react, leaving behind only carbon monoxide. Nevertheless, in the year 2021, high-resolution studies confirmed that the atmosphere does indeed contain a small but definite amount of water vapour, about 0.004% by volume. As the planet moves across the face of its star, it also produces what astronomers call the Rossiter-McLaughlin effect. This is seen as tiny shifts in the spectral lines of the star's light, caused by the planet blocking different parts of the rotating stellar surface. The strong gravitational tug of this heavy, close-orbiting planet causes its star to wobble noticeably, with a semi-amplitude of about 205 meters per second. Measurements showed that the planet's orbit is well aligned with the equator of its star, differing by less than 1 degree. This suggests the planet formed calmly within its original protoplanetary disk, rather than being violently disturbed by collisions with other planets. In the year 2008, astronomers thought that the planet's orbit might trigger stronger flares from its star whenever it passed a certain point. By the year 2010, some teams even claimed to detect regular X-ray flares tied to the planet's position. However, by the year 2019, after a careful analysis using data from the Arecibo Observatory, the MOST satellite and other telescopes, scientists concluded that earlier claims had been exaggerated. The host star simply does not show the right signs of strong flaring or active sunspot-like regions. In other words, there is no evidence that the star and planet interact magnetically. Over the years, astronomers have also searched for moons around HD 189 733b. A study in the year 2014 suggested there might be one, based on small changes in the planet's brightness, but this proposed moon would have been orbiting too far outside the planet's gravitational reach to be real. Later studies between the years 2019 and 2020 proposed possible volcanic exomoons, similar to Jupiter's moon Io, around HD 189 733b and other hot Jupiters. These claims were based on the detection of sodium and potassium gases that might have come from such moons. But a follow-up study in the year 2022 found no real evidence of any moons at all. Kelt 9b is one of the most remarkable exoplanets ever discovered, and it has become famous for being a place of extremes. It belongs to a class of planets known as ultra-hot Jupiters, which are giant gas planets that orbit extremely close to their host stars becoming far hotter than anything we can imagine from our own solar system. What makes Kelt 9b truly astonishing is not only its size and temperature, but also the unusual nature of the star it orbits. The host star is called Kelt 9, and it sits at a distance of about 670 light-years from our planet Earth. To give a sense of scale, a single light-year is the distance that light travels in 1 year, moving at almost 300,000 kilometers per second. That means the light we see from Kelt 9 today actually left that star nearly 7 centuries ago, long before telescopes even existed on Earth. Despite this enormous distance, astronomers were able to detect the planet using a specialized survey instrument known as the Kilodegree Extremely Little Telescope, or KELT for short. It was this instrument that gave the star and its planet their name. The existence of Kelt 9b was officially announced to the world in the year 2016, making it one of the most exciting discoveries of that period. By June of the year 2017, scientists had already determined that it was the hottest exoplanet ever detected. The star Kelt 9 itself is a very unusual host for a planet. Unlike our own Sun, which is a G-type main sequence star, Kelt 9 is classified between the B and A spectral types. In fact, it is described as being a late B-type or an early A-type star, falling into a rare transitional category, sometimes labelled as B9.5 to A0. What this means in simpler terms is that the star is much larger, brighter and hotter than our Sun. To put it in numbers, Kelt 9 is about 2 to 3 times larger in size and 2 to 3 times more massive in terms of weight than the Sun. Its surface temperature is measured at around 10,170 Kelvin, which is equal to approximately 9,897 degrees Celsius, or about 17,846 degrees Fahrenheit. This temperature is extremely high compared with stars that usually have planets orbiting them. Before the discovery of Kelt 9b, only a handful of A-type stars were known to host planets. Specifically, only 6 such stars had confirmed planetary systems, and among those the hottest one was the star WASP-33. However, even WASP-33 is significantly cooler than Kelt 9, with a surface temperature of 7,430 Kelvin, which is about 7,157 degrees Celsius, or roughly 12,914 degrees Fahrenheit. No B-type stars had ever been confirmed to host planets before Kelt 9, which means this discovery was groundbreaking. The possibility that Kelt 9 is the very first B-type star known to harbour a planet adds another layer of uniqueness to the system. The orbit of Kelt 9b is also extraordinary. The planet travels around its star in a nearly circular path, but the orbit is highly inclined relative to the star's rotation. The distance between the planet and the star is incredibly small, only 0.03462 astronomical units. An astronomical unit is the average distance between the Earth and the Sun, so this means Kelt 9b orbits its star at a distance that is less than 1/20th of the distance between Mercury and the Sun in our own solar system. Because it is so close, the planet completes a full orbit in less than 1.5 Earth days. That is astonishingly fast compared to Earth, which takes 365 days to circle the Sun. In terms of physical characteristics, Kelt 9b is a truly giant planet. It has a mass that is about 2.8 times greater than Jupiter, which itself is the largest planet in our solar system. However, despite being so massive, its radius is nearly double that of Jupiter. This means that the planet is puffed up or bloated, giving it a much lower density. In fact, its density is less than half that of Jupiter, which suggests that the extreme heat from the star is causing its atmosphere to swell. Like many hot Jupiters, Kelt 9b is tidally locked to its star. This means that the same side of the planet always faces the star, while the opposite side is permanently in darkness. This creates a world where one hemisphere experiences eternal scorching daylight, while the other lies in endless night. Such tidal locking is common in planets that orbit extremely close to their stars, because the strong gravitational forces gradually slow down the planet's rotation until it matches its orbital period. The atmosphere of Kelt 9b is being stripped away at an alarming rate. Because the planet is so close to such a hot and luminous star, it receives an intense bombardment of radiation. The outer layers of its atmosphere extend outward almost to the limit of what is known as its Roche lobe, the region around a planet where its gravity can hold onto material. Once the atmosphere reaches this boundary, it becomes easier for the gas to escape into space. This means that Kelt 9b is losing its atmosphere very rapidly, essentially evaporating under the fierce radiation of its star. In the year 2020, scientists were able to estimate the rate of this atmospheric loss, and it turned out to be astonishingly high, somewhere between 18 and 68 Earth masses for every billion years. If such a rate continues, the planet could eventually lose much of its gaseous envelope over astronomical timescales. As of the year 2022, the exact composition of Kelt 9b's atmosphere remains uncertain. However, researchers strongly suspect that it has a relatively low ratio of carbon to oxygen compared to other planets. This detail, while technical, is important because the balance between carbon and oxygen in a planet's atmosphere can greatly affect what kinds of molecules form and how the chemistry of the atmosphere develops. Despite the uncertainty in its detailed chemical makeup, one fact stands clear. Kelt 9b is the hottest exoplanet ever observed. The day side of the planet reaches temperatures of around 4,600 Kelvin, which corresponds to approximately 4,327 degrees Celsius, or about 7,820 degrees Fahrenheit. To put this in perspective, this makes the planet's day side hotter than some small stars known as K-type stars. In fact, the heat is so intense that molecules on the day side cannot remain intact. Instead, they are broken apart into their individual atoms. This allows normally hidden elements, those that usually condense into solid or liquid form on cooler planets, to exist freely as individual atoms. Among these are neutral oxygen, neutral and singly ionized iron, and singly ionized titanium. These atoms exist separately on the blazing day side, but when they are carried by atmospheric winds to the cooler night side, they recombine into molecules. This cycle of breaking apart and reforming is indirectly confirmed by observations that show the planet has a surprisingly high efficiency in transferring heat between its day and night sides. The efficiency is measured at about 0.3, and scientists think this is largely due to the energy released and absorbed as hydrogen molecules break apart and then recombine. Even more surprising, in the year 2021, astronomers took detailed spectra of the planet's atmosphere and discovered clear evidence of metal oxides and metal hydrides, combinations of metals with oxygen and hydrogen. This was unexpected because at such extreme temperatures, scientists did not think these compounds could survive. Later, however, when researchers used even higher resolution instruments, they did not detect any molecular emissions from the day side of the planet. This shows how challenging it is to study a place as extreme as Kelt 9b, where conditions push the limits of our physical understanding. Another fascinating feature of this planet is its thermosphere, which is the outermost atmospheric layer where temperatures rise dramatically with altitude. For Kelt 9b, models predict that the thermosphere can reach temperatures of between 10,000 and 11,000 Kelvin. This corresponds to about 9,727 degrees Celsius, up to 10,727 degrees Celsius, or in Fahrenheit, roughly 17,540 up to 19,340. These extraordinary temperatures are thought to be driven by the ionization of heavy atoms, such as iron, which absorb large amounts of energy from the star's radiation. The story of Kelt 9b is not just about numbers and measurements, it also represents a turning point in how astronomers view planetary systems. For many years, scientists assumed that giant planets like Jupiter could not exist around stars as hot as Kelt 9, because the radiation environment would simply be too harsh for a planet to form or survive. Yet the discovery of Kelt 9b proved that nature is capable of creating planets in even the most extreme conditions. This forces us to expand our ideas of where planets can exist and how diverse planetary systems may be throughout the galaxy. The incredible heat of Kelt 9b also challenges our understanding of atmospheric chemistry. On Earth, and even on the gas giants of our own solar system, molecules remain stable under ordinary temperatures. But on Kelt 9b, the rules are completely different. Elements that would normally be hidden away inside solid rocks or condensed deep within the atmosphere exist freely in gaseous atomic form. The winds that rush across the planet carry these atoms from one hemisphere to another, creating a continuous cycle of dissociation and recombination. This unique laboratory allows scientists to study atomic processes under conditions that are more like those found inside stars than inside planets. It is also interesting to reflect on how quickly Kelt 9b moves through space. Completing a full orbit in less than 1.5 Earth days means the planet is travelling at enormous speeds. To maintain such a tight orbit, Kelt 9b must move far faster than Earth, which averages around 30 kilometers per second around the Sun. The gravitational grip of Kelt 9 pulls it into this dizzying dance, leaving astronomers amazed at the resilience of the planet's atmosphere under such stress. Another striking aspect is the potential future of Kelt 9b. If it continues to lose mass at the current estimated rate, it could shrink significantly over time. While 1 billion years may seem unimaginably long to us, in the lifetime of a star it's not all that much. The host star itself is far more massive than the Sun, and will therefore burn out much more quickly, living for only a few 100 million years more. This means the entire system is temporary on cosmic timescales, and Kelt 9b may one day be stripped down to a rocky or metallic core, or even consumed by its star. What makes Kelt 9b so captivating to astronomers and the public alike is not just its extreme properties, but the way it defies expectations. It is hotter than many stars, larger than Jupiter, and located around a star that no one thought could host a planet. Its atmosphere is vanishing into space, yet it persists. It shows us that the universe is capable of creating worlds that challenge the boundaries of our knowledge, pushing science into new territory with every discovery. Gliese 581c is a planet that orbits a star in the Gliese 581 system. It was the second planet found in that system, and is the third one from its parent star in order. This world is much heavier than Earth. Its mass is about 6.8 times greater than that of our own planet. Because of this, astronomers classify it as what is known as a super-Earth, a type of planet that is larger than Earth, but not as enormous as the giant planets like Neptune or Jupiter. When it was first announced in the year 2007, Gliese 581c immediately caught the attention of astronomers around the world. It was thought to be the very first planet discovered in the so-called habitable zone of its star, meaning it might have had just the right temperature to keep water in liquid form on its surface, since liquid water is one of the most important requirements for life. This raised the thrilling possibility that the planet might support at least some hardy extreme forms of life, similar to certain microbes found on Earth. However, later studies painted a less hopeful picture. Newer and more accurate models of habitable zones suggested that Gliese 581c is likely much too hot for life as we know it. Even though it is not a good candidate for life, the planet and its system are still very important because of how close they are to us in cosmic terms. The star Gliese 581 is only about 20.55 light-years away from Earth, which equals roughly 194 trillion kilometers, or about 121 trillion miles. It lies in the sky in the direction of the constellation Libra. Astronomers can pinpoint its location very precisely in our Milky Way galaxy by using its declination and right ascension coordinates. The Discovery team announced their findings in a paper dated the 27th of April in the year 2007, which was later published in the July issue of the journal Astronomy and Astrophysics. At that time, Gliese 581c was reported to be the very first planet that seemed Earth-like in the habitable zone of its star, and it was also the smallest planet yet found orbiting a normal star. But 2 years later, on the 21st of April in the year 2009, astronomers discovered an even smaller planet in the same system, named Gliese 581e. That one had a mass of about 1.9 times that of Earth. The same paper also confirmed the existence of another planet, Gliese 581d, which had a minimum mass of about 7.7 Earths, and orbited its star at a distance of about 0.25 astronomical units, roughly 1/4 of the distance between Earth and the Sun. The presence of Gliese 581c, as well as its mass, was detected using a technique called the radial velocity method. This method works by watching how the host star, Gliese 581, wobbles slightly due to the gravitational tug of its planets. By carefully studying these tiny regular wobbles, astronomers can calculate the minimum mass of each planet. For Gliese 581c, the minimum mass was estimated to be about 5.5 times that of Earth. The radial velocity method cannot directly tell the exact mass of the planet, only the minimum. But astronomers know it cannot be much heavier, because if it were, the entire planetary system would become unstable. Computer simulations of the orbits of the planets in the system, under the assumption that they all orbit in nearly the same plane, suggest that none of the planets can have more than about 1.6 to 2 times their minimum masses. If they were any heavier than that, the gravitational pulls would throw the system out of balance, especially because of the strong interactions between planets Gliese 581e and Gliese 581b. This means that the upper limit for Gliese 581c's mass is about 10.4 times the mass of Earth. A study carried out in the year 2024 helped refine these calculations. It measured the tilt of the planet's orbit, something known as its inclination, and with that information, scientists were finally able to estimate the planet's true mass. They found it to be about 30% greater than the earlier minimum value, giving it a mass of about 6.8 times that of Earth. Unlike some other exoplanets, Gliese 581c does not pass directly in front of its star from our point of view here on Earth. Because of this, astronomers cannot measure its radius using the transit method, and since the radial velocity method only provides mass, there are limits to what scientists can say about its size and internal structure. Still, they can make educated guesses using theoretical models. If the planet really has a mass of about 6.8 Earths, and if it is a rocky world with a large iron core, then it might have a radius about 50% larger than Earth's. In such a case, the pull of gravity on its surface would be more than twice as strong as the gravity we experience on Earth, about 2.24 times stronger to be exact. On the other hand, if Gliese 581c is not a rocky world, but instead is covered in water and ice, then its radius would likely be less than twice that of Earth's. Even with a thick outer ocean-like shell, its surface gravity would still be at least 1.25 times stronger than Earth's. Scientists suggest that the real radius of the planet probably lies somewhere between these two extreme possibilities. Other researchers have put forward different ideas about the nature of Gliese 581c and planets like it. For example, Sarah Seeger, an astronomer at the Massachusetts Institute of Technology, speculated that planets of around 5 Earth masses could take on several exotic forms. Some could be giant rocky worlds made mostly of silicate minerals, which she called rock giants. Others might be solid iron worlds, cannonball planets. Some could be small gas planets, rich in hydrogen and helium, called gas dwarfs. Still others might be made largely of carbon and could even form diamond worlds. There are also stranger possibilities, such as planets composed of exotic ice at high pressures, so-called Ice-7 worlds, or planets made largely of carbon monoxide. Unfortunately, measurements from the Canadian-built Space Telescope MOST showed that Gliese 581c does not pass in front of its star, meaning no transits are seen from Earth. Without transits, measuring its radius directly is impossible. Even so, Gliese 581c remains an important subject of study. Recent research suggests that planets in the super-Earth category do not evolve in the same way as the rocky inner planets of our solar system, such as Earth, Venus, or Mars. Instead of shedding their thick atmospheres over time and becoming mainly rocky with only a thin layer of air, many super-Earths seem to retain their thick envelopes of hydrogen and other gases. If that is the case, then Gliese 581c might not resemble Earth at all, but instead be a rocky core permanently buried under a heavy, suffocating blanket of gas. Gliese 581c is a fascinating world that orbits its parent star very quickly. Instead of taking one full year like Earth does, it completes a full orbit around its star in only 13 Earth days. This means that what would be considered a year on Gliese 581c lasts less than 2 weeks by our standards. The planet circles at a distance of about 11 million kilometres from its star. To compare, Earth travels at a distance of about 150 million kilometres from the Sun. At first, one might think that being so close to a star would make Gliese 581c unbearably hot, but its host star is very different from our Sun. The star is a red dwarf, smaller and cooler than the Sun, and it shines with much less brightness. Because of this, the distance at which Gliese 581 orbits actually places it on the inner warmer edge of what astronomers call the habitable zone. This zone is the range of distances from a star where a planet could, at least in theory, have liquid water on its surface. However, being in the habitable zone does not automatically mean that the planet would be comfortable or suitable for human life. Human habitability requires a very specific and narrow set of conditions. In fact, based on newer and more refined models, Gliese 581c is probably far too hot to support life as we know it. To imagine how the star would appear from this planet, scientists compared the apparent size of Gliese 581 to our Sun. The radius of a typical star like Gliese 581, considering its age and composition, is about 0.00128 astronomical units, whereas the Sun's radius is about 0.00465 astronomical units. What this means visually is striking. If someone stood on the surface of Gliese 581c and looked up at the sky, the star would look about 3 3/4 times wider than our Sun appears from Earth, and it would cover an area in the sky about 14 times greater. Because the planet orbits so close to its star, astronomers believe it is tidally locked. This means that one side of the planet always faces the star, experiencing perpetual daylight, while the opposite side remains in eternal night. It is the same phenomenon that keeps our moon showing the same face to Earth. Some studies suggest the orbit of the planet is nearly circular, but earlier models proposed that its orbit could be somewhat oval, or eccentric, with eccentricity values between 0.10 and 0.22. If the orbit were indeed eccentric, the planet would experience extreme stretching and squeezing forces, a process known as tidal flexing. Such forces could generate enormous internal heating. In some cases, like Mercury in our solar system, planets under strong tidal influences can rotate in patterns that are not perfectly synchronized with their orbit. Mercury, for example, rotates 3 times for every 2 orbits around the Sun. Even if Gliese 581c is tidally locked, it would still experience a subtle rocking motion known as libration, which would cause the boundary between night and day to shift slightly over time. Over the ages, tidal heating may have had a dramatic effect on the planet's geology. Models suggest that Gliese 581c could release a heat flow up to 3 times greater than that of Io, one of Jupiter's moons. Io is the most volcanically active body in our solar system, so if Gliese 581c has even more tidal heating, its surface might be riddled with volcanoes, lava flows, and even active tectonic plates shifting beneath its crust. Not all scientists agree on whether this planet could ever have been habitable. A team led by von Blow concluded that Gliese 581c is simply too close to its star and lies outside the true habitable zone. Another study, led by Celsus and colleagues, pointed out that even being inside the habitable zone does not mean a planet is truly habitable. They emphasised that Gliese 581c is beyond the conservative boundaries of habitability. If it ever had liquid water, that water was likely lost long ago when its parent red dwarf star emitted strong X-rays and powerful ultraviolet radiation. According to these studies, the surface temperature of the planet might range anywhere from about 700 Kelvin to 1000 Kelvin. That is, from roughly 427 degrees Celsius to about 727 degrees Celsius. These values are very similar to those on Venus today, which is scorching and hostile. Other scientists try to estimate the temperatures by calculating the energy output of the star. Gliese 581 shines with only about 0.013 times the brightness of the Sun. Using this, scientists estimated what is called the effective temperature, or black body temperature, of the planet. Assuming the planet reflects as much light as Venus, about 64%, its temperature would be around -3 degrees Celsius. If it reflects light more like Earth, with about 29.6%, its temperature would be about 40 degrees Celsius. These values fall within the range where water could remain liquid. But this is only a rough estimate. The actual surface temperature can be much higher because of the greenhouse effect. On Venus, for example, the effective temperature is about -41 degrees Celsius, yet its real surface temperature is a blistering 464 degrees Celsius, a difference of more than 500 degrees. This happens because Venus has an atmosphere that is over 96% carbon dioxide, which traps heat extremely effectively. For Gliese 581c, many scientists believe that something similar would happen. Instead of being a comfortable Earth-like world, it may have undergone a runaway greenhouse effect, turning into a furnace like Venus. This runaway effect would trap heat and make the planet far too hot for life as we know it. Still, there are a few interesting possibilities. If the planet's day side were covered in thick, highly reflective clouds, those clouds could bounce much of the incoming light back into space, helping to cool it down. Alternatively, if the surface were coated in ice, the planet would reflect even more sunlight and stay cooler. But this icy state would be very unstable. The moment volcanic activity released carbon dioxide, or sunlight melted even a little ice and released water vapour, a runaway greenhouse effect would quickly return. For such an icy condition to persist, the planet would need an extremely high reflectivity, greater than 95%. which is unlikely for any natural world. Gliese 581c, one of the most famous discovered exoplanets, is thought to be located outside what scientists call the habitable zone, the region around a star where liquid water could naturally exist on a planet's surface. So far, no clear proof has been found that water exists there, and it is very unlikely that any of it remains in liquid form. In the future, advanced techniques, similar to those used to study the atmosphere of another planet called HD 209458b, might allow astronomers to detect water vapour in the atmosphere of Gliese 581c. However, this method only works for planets that pass directly in front of their star from our viewpoint, creating what is known as a transit. Gliese 581c does not appear to transit its star, so such a study may not be possible. Computer simulations and theoretical models suggest that if volatile substances such as water or carbon dioxide were present on the planet, they would behave in strange and extreme ways due to the planet's environment. On the scorching hot side facing the star, these substances might evaporate into gas. Strong winds could then carry the vapours across the planet to the cooler, dark side, where they might freeze and settle as enormous ice caps. Over very long periods, the entire atmosphere could gradually migrate and freeze onto the night side, leaving the sunlit side bare and airless. Yet, scientists still do not know for sure if Gliese 581c has water or carbon dioxide at all. There is also another possibility. If the planet possesses a thick, stable atmosphere, the winds within it could distribute the heat more evenly around the globe. In that case, a much larger area of the surface might be capable of supporting conditions closer to habitability. To understand this idea, astronomers often compare Gliese 581c to our neighbouring planet Venus. Venus has only a very small tilt on its axis, which means its poles receive very little direct sunlight. In addition, Venus rotates extremely slowly, taking about 117 times longer to complete one rotation than Earth does. This slow spin creates long days and long nights. Even though sunlight falls unevenly on Venus, blazing on the day side and almost absent on the night side, the powerful globe-spanning winds in its thick atmosphere carry the heat everywhere. As a result, the polar regions and the night side of Venus remain nearly as hot as the sunlit side. Something similar might happen on Gliese 581c if its atmosphere is dense enough. Adding to the intrigue of this distant world, humanity once tried to reach out to it. On the 9th of October in the year 2008, a powerful digital radio transmission called a Message from Earth, or AMFE for short, was aimed directly at Gliese 581c. This signal acted like a kind of time capsule, carrying 501 individual messages. These messages were chosen through a global competition organised on the social networking platform Bebo. The transmission was sent using the enormous RT-70 radar telescope in Ukraine, operated by the State Space Agency of Ukraine. If the signal continues its journey without interruption, it is expected to arrive at Gliese 581c in the early part of the year 2029. More than 500,000 people from around the world, including well-known celebrities and politicians, contributed to this extraordinary project. What made the AMFE effort so unique was that it became the world's very first digital time capsule in which the contents were selected directly by ordinary people, rather than by scientists or officials. Gliese 581c has not only captured the attention of astronomers and planetary scientists, but has also become a kind of cultural icon, a faraway world that humanity has reached out to with words and thoughts, hoping that someday a response might echo back across the vastness of space. HAT P7b, which is also known as Kepler 2b, is one of the most extraordinary planets ever found beyond our solar system. It belongs to the family of worlds we call exoplanets, planets that do not orbit our Sun, but rather circle around distant stars light years away from us. This fascinating world was first discovered in the year 2008, and since then it has become one of the most studied and talked about planets outside of our solar system. From the moment of its discovery, astronomers realised that it was not just another distant planet, but something far more unusual, extreme, and even a little mysterious. The first thing that makes HAT P7b stand out is how close it travels to its parent star. Unlike Earth, which circles the Sun from a safe distance of about 150 million kilometres, HAT P7b practically hugs its star, orbiting in such a tight path that its entire year lasts just over 2 days. Because of this closeness, it is bombarded with enormous amounts of heat and energy from its star, far more than what any planet in our solar system receives. As a result, this giant world is not only larger and more massive than Jupiter, the king of our own planetary family, but it is also blazing hot, with a climate so extreme that it almost defies imagination. Scientists have tried to estimate what the temperatures on this exotic world must be like, and their findings are staggering. On the side of the planet that always faces its star, the so-called day side, temperatures are thought to reach between 2630 and 2880 Kelvin. If we were to translate those numbers into more familiar measurements, that equals about 4,270 to 4,720 degrees Fahrenheit, or about 2,360 to 2,610 degrees Celsius. These fiery conditions are hot enough to melt metals like iron or nickel, and far hotter than the surface of Venus, the hottest planet in our solar system. But HAT P7b does not cool off very much even on the night side. On the half of the planet that faces away from the star, temperatures still range between 2,211 and 2,238 Kelvin. That equals about 3,520 to 3,569 degrees Fahrenheit, or about 1,938 to 1,965 degrees Celsius. In other words, no matter where you go on this strange world, you would be surrounded by a hellish oven that never truly cools down. But the extreme heat is only the beginning of this planet's unusual story. HAT P7b has another feature that makes it even stranger. It is one of the darkest planets ever observed in the universe. Scientists measure how much light a planet reflects with something called albedo. An albedo of 1 means that an object reflects all of the light that hits it, like a perfect mirror, while an albedo of 0 means that the object reflects nothing at all, like a pitch-black surface. Earth, for instance, reflects about 30% of the sunlight that strikes it, giving our world an albedo of about 0.3. HAT P7b, by contrast, reflects less than 3% of the light it receives. That means that more than 97% of the starlight striking it is swallowed into its atmosphere or surface. Imagine a giant, burning, superheated ball of gas that, despite its fiery temperature, looks nearly as black as coal when seen from space. It is an image that makes HAT P7b feel even more alien and mysterious. The discovery of this bizarre world was no simple feat. It began with the HATNet project, an ambitious program that set up telescopes in different parts of the world to scan the skies for signs of planets crossing in front of their stars. The project used several robotic instruments, including HAT7, which was located at the Smithsonian Astrophysical Observatory's Fred Lawrence Whipple Observatory in Arizona, and HAT8, which was installed on the rooftop of the Smithsonian Astrophysical Observatory's submillimeter array building, on top of the great volcano Mauna Kea in Hawaii. These telescopes, night after night, pointed their eyes toward the heavens and took thousands upon thousands of images in search of tiny dips in starlight that might mean a planet had passed in front of its star. Between late May and early August of the year 2004, these telescopes turned their gaze toward a patch of sky labelled HATNet Field G154. In this single region, they observed about 33,000 stars almost every night. From their patient work, they collected a staggering 5,140 individual exposures. After carefully analysing these images, astronomers noticed something remarkable. One particular star, named GSC 03547-01402, seemed to dim in brightness at very regular intervals. Each time its light dropped by about 7 millimagnitudes, a small but detectable change, and the pattern repeated every 2.2047 days. Each dimming event lasted about 4.1 hours, which suggested strongly that a planet was passing directly in front of the star, blocking a tiny fraction of its light as it moved along its orbit. This star would later be officially designated HAT P7, with the P indicating that it was part of the planetary discoveries of the HATNet program. The discovery was made even more reliable because of an extraordinary coincidence. The star HAT P7 happened to sit in an overlapping region between two fields observed by different HATNet telescopes, labelled G154 and G155. This meant that independent observations could be made of the same star, reducing the chance of mistakes or false detections. The HAT-6 telescope in Arizona and the HAT-9 telescope in Hawaii were able to confirm the transit signal by observing the neighbouring field G 155. From late July 2004 to late September 2005, they gathered an additional 11,480 exposures. Combined with the earlier data, this created a massive set of 16,620 data points, enough to confirm beyond doubt that a planet was indeed orbiting this distant star. Not long afterward, another great leap forward came from space itself. The star HAT P7 and its newly discovered planet were located within the very first field of view of the legendary Kepler mission spacecraft. This satellite was specifically designed to hunt for planets by staring at stars for long periods of time and measuring their tiny fluctuations in brightness. When Kepler turned its sensitive detectors toward HAT P7, it confirmed the existence of the planet with a confidence and precision that ground-based telescopes could never achieve. Kepler not only nailed down the planet's orbital properties with greater accuracy, but also observed what happened when the planet disappeared behind its star. These occultation measurements revealed that HAT P7b had an atmosphere that strongly absorbed light and did not move heat efficiently from the day side to the night side. In other words, the planet's skies trapped the heat on the side facing the star, leaving the dark side still scorching but comparatively cooler. The successful testing on HAT P7b also proved that Kepler's instruments were powerful enough to detect planets much smaller than gas giants, even Earth-like planets in habitable zones. As the years passed, HAT P7b continued to fascinate astronomers. On the 4th of July in the year 2011, this remarkable world became part of history when the Hubble Space Telescope made its 1 millionth scientific observation by studying it. That milestone alone shows how important HAT P7b has been in advancing our knowledge of distant worlds. But the surprises did not stop there. In August of the year 2009, scientists announced that HAT P7b might have something incredibly unusual: a retrograde orbit. Normally, planets orbit their stars in the same direction that the star itself spins, much as the planets of our solar system orbit in the same direction that the Sun rotates. A retrograde orbit, by contrast, means that the planet goes around the star in the opposite direction of the star's rotation. To detect this, astronomers use something called the Rossiter-McLaughlin effect, which measures tiny changes in starlight as a planet passes across the spinning face of its star. Their results suggested that HAT P7b was not just orbiting close to its star, but it was doing so while moving against the natural flow. This announcement came just one day after the first discovery of a retrograde orbit in another planet, WASP-17b. Later studies, including one in the year 2012, strengthened the case. They measured the angle of the orbit compared to the star's rotation axis, and found it to be about 155 degrees, with a margin of error of 37 degrees. Such a tilted and reversed orbit is rare, and points to a chaotic and violent history for this planet. Astronomers believe that HAT P7b may not have always been in its current position. In fact, it likely formed much farther away from its star, possibly at a distance of around 3 astronomical units, that is, 3 times the average distance between Earth and the Sun. But gravitational forces from other objects in the system seem to have dragged it inward over time. The star HAT P7 has at least 2 other stellar companions. One of them, HAT P7c, is a red dwarf star that orbits HAT P7a, the main star, at a distance of about 32 astronomical units. Its orbit is highly eccentric, meaning it moves in a stretched oval path. The other companion, HAT P7b, lies much farther away, at about 700 astronomical units. Astronomers think that the outer star may have triggered a Kozai mechanism, a process where the gravitational tug of a distant object stirs up the orbital eccentricity of an inner companion. This chain of gravitational chaos could have pushed HAT P7b into a more and more eccentric orbit until tidal forces eventually circularized it, locking it into its present, dangerously close retrograde path. In January of the year 2010, another discovery about HAT P7b made headlines. For the first time, scientists detected what are called ellipsoidal light variations from this planet. This effect happens when a massive planet's gravity tugs on its host star strongly enough to distort the star's shape. Instead of being a perfect sphere, the star becomes stretched, more like an ellipsoid. As the star rotates, its brightness changes slightly, and these variations can be measured. Detecting this effect around HAT P7b not only added to our knowledge of the system, but also showed just how powerful the gravitational connection is between the star and its close orbiting planet. Years later, in December of the year 2016, a team of scientists led by Dr. David Armstrong published a remarkable letter in the journal Nature Astronomy. They reported evidence that HAT P7b experiences strong winds that change speed dramatically over time. These winds are thought to circle the planet, shifting the brightest point on the planet's atmosphere by large amounts. What is especially fascinating is how quickly these changes happen, sometimes over just tens of days, sometimes over hundreds. This suggested that the planet's global wind patterns and cloud coverage are not stable, but rather highly variable. Models of the atmosphere even predict that on the night side, exotic forms of precipitation might occur. Instead of rain made of water, the atmosphere might contain droplets or crystals of aluminum oxide, the mineral known as corundum. This mineral is famous on Earth because it forms precious stones like rubies and sapphires. Imagine, then, a world where clouds are made not of water vapour, but of minerals that on Earth we would treasure as gemstones. In the skies of HAT P7b, storms of sparkling crystals could sweep across the night, creating one of the most surreal and beautiful yet deadly alien weather systems imaginable. All of these discoveries paint a picture of a planet that is as extreme as it is fascinating. HAT P7b is larger and more massive than Jupiter, hotter than any furnace we could imagine, darker than charcoal despite its high temperatures, and filled with wild weather and strange clouds that rain gemstones. It orbits its star backward, as if defying the natural order, and it likely travelled inward from a much farther orbit in a cosmic dance driven by the pull of other stars. Its study has marked many milestones in astronomy, from being among the first major successes of the Kepler mission, to being the target of the Hubble Space Telescope's millionth observation, to revealing new ways we can study exoplanets through light variations and atmospheric shifts. In a universe filled with billions of stars and planets, HAT P7b reminds us just how diverse and unexpected other worlds can be. If we thought planets were only like those in our own solar system, this distant giant shattered that belief. Instead, it shows us that nature can create worlds so exotic that they seem to belong in science fiction rather than in real life. Yet, thanks to the persistence of astronomers and the powerful tools they have built, we know that HAT P7b is very real. And as our technology improves, it will not only continue to reveal its secrets, but also guide us toward understanding countless other strange and wonderful planets that orbit the distant stars. Far beyond our own solar system, in the wide starry stretch of the constellation known as Pegasus, there lies a remarkable world that changed the history of astronomy forever. This world is called 51 Pegasi b, though today it is more often referred to by its official name, Dimidium. This strange and beautiful planet is not one that can be seen with the naked eye from Earth, for it rests at a distance of about 50 light-years, which is equal to roughly 15 parsecs from where we live. Though that distance sounds unimaginably far, in cosmic terms it is not too distant, and astronomers are able to study it with their powerful instruments. Dimidium, or 51 Pegasi b, is one of the most extraordinary discoveries in all of modern science. It was the very first planet ever detected orbiting a star that is similar to our own Sun, a type of star that astronomers call a main sequence star. Before this moment, no one had ever confirmed the existence of such a planet outside our solar system. The announcement of its discovery shook the scientific world in the mid-1990s, proving that our solar system was not unique, and that planets truly do exist around other stars. The star it orbits is called 51 Pegasi. The name itself comes from the system of designations introduced by the English astronomer John Flamsteed, who numbered stars according to their positions within constellations. The discovery of a planet circling this star marked a turning point in the exploration of the universe. Suddenly, what had been the subject of speculation and imagination for centuries became a confirmed reality. Astronomers realized that the galaxy might be teeming with other worlds, perhaps even ones similar to our own. The story of Dimidium begins in the year 1995. Two Swiss astronomers, Michel Mayer and Didier Queloz, working at the University of Geneva, made the groundbreaking announcement on the 6th of October of that year. They published their findings in the scientific journal Nature. Using a method known as radial velocity, they were able to detect the presence of a large planet orbiting close to 51 Pegasi. This method involved the use of a highly sensitive spectrograph called LED, which was mounted on a telescope at the Observatoire de Haute-Provence in France. What the scientists noticed was that the light from the star shifted in a regular pattern. The spectral lines, which are like the fingerprints of light that tell astronomers about the elements and movements of a star, were changing slightly back and forth. These shifts revealed that the star was wobbling, pulled by the gravitational tug of an unseen companion. The changes they observed were around 70 meters per second, a subtle but steady movement that betrayed the existence of a planet, orbiting very close to the star at a distance of only about 7 million kilometers. The announcement caused an immediate sensation. Within just a week, another team of astronomers in California, using the famous Lick Observatory, confirmed the discovery. Soon after, other observatories around the world followed, adding further evidence. The discovery was so significant that many years later, in the year 2019, the Nobel Prize in Physics was awarded to Mayer and Queloz for this achievement, honouring their work that opened up a whole new frontier in astronomy. When this planet was first discovered, it seemed very strange. It completed an orbit around its star in only about 4 Earth days. This meant that it was incredibly close to its star, even closer than Mercury is to the Sun in our solar system. To circle so quickly, the planet had to be moving at a staggering speed of about 136 kilometers per second, which is close to 300,000 miles per hour. The mass of the planet was measured to be about half that of Jupiter, the giant of our own solar system, or roughly 150 times the mass of Earth. This was a shock. At the time, astronomers had assumed that massive planets like Jupiter could only exist far from their stars, beyond a certain boundary where gases and ices could condense during planet formation. Yet here was a giant planet, almost as big as Jupiter, orbiting extremely close to its star. It did not fit any of the accepted theories. Scientists even speculated at first that perhaps this world was not a true planet, but instead the remnant of a failed star, perhaps the stripped core of a brown dwarf. But as more was learned, it became clear that it was indeed a gas giant, a true planet, though one very different from what astronomers had expected. Because of this discovery, a whole new category of planets had to be created. Dimidium became the prototype for a class of worlds known as hot Jupiters. These are giant planets, similar in mass to Jupiter or sometimes even larger, that orbit extremely close to their stars and are heated to extreme temperatures. Since the mid-1990s, many more such hot Jupiters have been found, orbiting stars such as 55 Cancri and Tau Bootis. The discovery of these planets forced astronomers to rethink how planetary systems form and evolve. Theories of orbital migration, the idea that giant planets may form far out in a star system and then gradually move inward, gained strength as a way to explain these puzzling worlds. The conditions on Dimidium are extreme beyond imagination. If one assumes the planet is perfectly grey, with no greenhouse or tidal effects, and with a bond albedo of 0.1, then its temperature would be about 1,265 kelvins, which is about 992 degrees Celsius, or 1,817 degrees Fahrenheit. This places it in the same temperature range as other famous hot Jupiters, such as HD 18973b and HD 29458b, though the exact temperatures of those worlds vary between about 1,180 kelvins to 1,392 kelvins. This means that the atmosphere of Dimidium is likely puffed up into a thick, extended layer of heated gases. Though the planet has less mass than Jupiter, its radius is probably larger, simply because the extreme heat causes the gases to expand. The atmosphere may contain clouds of silicate particles, minerals that on Earth make up rocks, which could condense in the scorching skies. Beneath this glowing outer layer, the gases of the planet would be heated to such a degree that the planet itself might shine faintly red. The planet is also thought to be tidally locked to its star. This means that, like our moon with the Earth, it always keeps the same face turned toward its star. One side of Dimidium is bathed in perpetual daylight and blazing heat, while the other side remains in eternal darkness. Such a situation leads to fierce winds and violent atmospheric dynamics as heat tries to flow from the day side to the night side. Over the years, scientists have tried to study Dimidium more closely, though it is a challenging task because the planet does not transit across the face of its star from our point of view. That means astronomers cannot observe the dimming of starlight as they can with many other exoplanets. Still, in the year 2015, a team claimed to detect the planet in the visible light spectrum using the HARPS spectrograph at the La Silla Observatory in Chile, which belongs to the European Southern Observatory. If confirmed, this detection suggested that the planet had a mass of about 0.46 Jupiter masses and might have a very high albedo, meaning it reflected a great deal of light. This would have given it a large radius, up to about 1.9 Jupiter radii, and classified it as an inflated hot Jupiter. However, later observations could not replicate these results. By the year 2020, studies suggested that the planet's albedo was likely below 0.15, meaning it was much darker than he initially thought. More recent measurements, made in the year 2021, detected a marginal signal of polarized reflected light. While these results were intriguing, they could not precisely determine the albedo without more assumptions about how the atmosphere scattered light. The consensus that has emerged in the past few years is that Dimidium is a low albedo planet, probably with a radius of around 1.2 Jupiter radii. In addition to its scientific significance, Dimidium also has an interesting history when it comes to its name. At first, following the standard convention, it was simply called 51 Pegasi b, meaning it was the first planet found orbiting the star 51 Pegasi. In the year 1996, the American astronomer Geoffrey Marcy, who was among the early pioneers of exoplanet research, suggested the informal nickname Bellerophon. This name came from Greek mythology, from the hero who rode the winged horse Pegasus, which connected beautifully with the star's constellation. Years later, in July of the year 2014, the International Astronomical Union, which is the official body responsible for naming celestial objects, launched a project called Name Exoworlds. This project allowed the public to take part in naming certain exoplanets and their host stars. People from around the world could suggest names, and then the public would vote. By December of the year 2015, the results were announced. The winning name for 51 Pegasi b was Dimidium, a word submitted by the Astronomische Gesellschaft Luzern, or Astronomical Society of Lucerne in Switzerland. The word Dimidium comes from Latin and means half, referring to the planet's mass being about half that of Jupiter. In the year 2017, astronomers announced that they had found traces of water in the atmosphere of Dimidium. This was an exciting discovery, for although the planet is far too hot to have liquid water or to support life as we know it, the detection of water molecules in its atmosphere showed just how advanced exoplanetary science had become since the initial discovery. And in the year 2019, as already mentioned, the discovery of Dimidium was recognised at the highest level when Michel Mayor and Didier Queloz received the Nobel Prize in Physics, partly for their work in finding this remarkable world. Dimidium's story is more than just the tale of a single planet. It represents the beginning of a new era. Before its discovery, the question of planets around other stars was a matter of speculation. Some scientists believed that planets must exist elsewhere, while others doubted it could be proven. After 1995, everything changed. The floodgates opened, and hundreds, then thousands, of other exoplanets were discovered. Today, with space telescopes such as Kepler, TESS, and the James Webb Space Telescope, astronomers know of many thousands of exoplanets, with many more waiting to be confirmed. Dimidium was the first, the pioneer that showed us we are not alone in having planets. This extraordinary world, glowing in the constellation of Pegasus, continues to inspire scientists and the public alike. Though no spacecraft has yet visited it, and perhaps none will for centuries, its existence has changed our understanding of the universe. Kepler-16b, formerly called Kepler-16, ABB, is a planet outside our solar system that has fascinated astronomers and captured the imagination of the public. Unlike Earth, which is made mostly of solid rock, or Jupiter, which is mostly gas, Kepler-16b is something in between. It is a world about the mass of Saturn, and its bulk is made of both gas and heavier materials such as rock and ice. This mixture makes it a strange world, neither purely solid nor purely gaseous, but balanced between the two. Scientists often describe it as being half gas and half rock and ice, a hybrid giant that reflects the richness of planetary diversity in the universe. The most extraordinary feature of Kepler-16b is not just what it is made of, but where it orbits. This planet does not circle a single star like Earth goes around the Sun. Instead, it travels around two stars at once, a binary star system known as Kepler-16. These two suns dance around each other in their own tight orbit, completing a circuit every 41 days. Together, they create a shared centre of gravity, and Kepler-16b follows a path around this combined centre. The planet takes about 229 days to complete one full trip, something very similar to how Venus orbits our own Sun. This arrangement makes Kepler-16b the very first confirmed and unambiguous example of what astronomers call a circumbinary planet, a world that orbits not one star but two. Josh Carter of the Center for Astrophysics at Harvard and the Smithsonian Institution, one of the astronomers who helped discover the planet, explained the significance by saying, "It is the first clear case where we have seen a planet moving around two stars. For many decades, such a possibility had been the stuff of science fiction, most famously shown in the Star Wars films where the desert world of Tatooine has two suns rising above its horizon. Yet in 2011, science caught up with fiction, and a real Tatooine was revealed in the heavens. What makes Kepler-16b even more unusual is that it exists in a region where many scientists once thought planets could not form. According to Sarah Seeger, a planetary scientist at the Massachusetts Institute of Technology, the prevailing idea was that for a planet to survive in a binary star system, it would need to orbit at a safe distance. The rule of thumb suggested that the planet should be at least 7 times farther from the two stars than the stars were from each other. That wide gap was considered necessary for stability. Yet Kepler-16b breaks this supposed rule. Its orbit is only about half that distance. The discovery showed that nature is more inventive than our theories, and that planets can indeed thrive in places where scientists once thought they could not. When astronomers looked at the details of its position, they found that Kepler-16b lies near the outer edge of what is called the habitable zone of its system. The habitable zone is the range of distances from a star where liquid water could, in principle, exist on a planet's surface. On Earth, liquid water is essential for life, so the idea of the habitable zone is closely tied to the search for extraterrestrial life. However, Kepler-16b is a gas giant, similar in size to Saturn, and it does not have a solid surface where oceans or continents could form. Its atmosphere is extremely cold, with surface temperatures ranging between about -100 and -70 degrees Celsius, or about -150 to -94 degrees Fahrenheit. Such conditions are far too frigid for liquid water or life as we know it. The planet was discovered in the year 2011 using the Kepler Space Telescope, a powerful observatory launched by NASA to search for planets outside our solar system. The spacecraft used the transit method, a technique where scientists watch for tiny dips in the brightness of a star as a planet passes in front of it. What was striking in this case was that astronomers noticed dimming in one of the stars of the Kepler-16 system, even at times when the other star was not eclipsing it. This indicated the presence of another body, a planet. What made the discovery even more remarkable was the level of precision that scientists could achieve in measuring the characteristics of the system. By carefully analysing the timings of eclipses between the two stars and the transits of the planet, astronomers were able to determine the sizes and masses of all three objects with an accuracy that was unprecedented at the time. Lawrence Doyle of the SETI Institute in Mountain View, California, who led the discovery team, proudly declared, "I believe this is the best measured planet outside the solar system." For example, the radius of Kepler-16b was determined to within just 0.3%, a degree of accuracy better than for any other exoplanet known at that time in September of 2011. From Earth's perspective, the situation changed over time. Kepler-16b was seen transiting across the dimmer star until the year 2014, after which those events ceased. Then, until the year 2018, the planet could still be observed crossing in front of the brighter star. After that, the alignment shifted, and the planet no longer passed in front of either star from our point of view. This means that by the transit method, Kepler-16b has become invisible to us. It will not be seen again in this way until around the year 2042, when the geometry of the system aligns once more. The story of Kepler-16b did not end there. In the year 2021, astronomers made another milestone discovery. Kepler-16b became the first circumbinary planet to be detected using a completely different technique, the radial velocity method. This method measures the slight wobble of stars as they are tugged by the gravity of orbiting planets. The fact that Kepler-16b could be confirmed through both transit and radial velocity techniques added great confidence to its measurements. 2 years later, in the year 2023, another circumbinary planet called TOI 1338c was also confirmed using this method, making Kepler-16b the trailblazer in a new era of discoveries. In terms of physical size and nature, Kepler-16b is classified as a gas giant. Its mass and radius are close to those of Jupiter and Saturn, the two largest planets in our solar system. Its temperature is about 188 Kelvin, which corresponds to minus 85 degrees Celsius, or minus 121 degrees Fahrenheit. The planet has a radius equal to about 77% of Jupiter's radius, making it slightly smaller than Saturn. With no solid surface, it is a swirling ball of gases, likely made of hydrogen, helium, and other elements. Its parent stars, which it circles in a circumbinary orbit, are two very different suns. One is a K-type star, orange in colour and cooler than our Sun. The other is a smaller M-type red dwarf. Together they orbit each other every 41 days. The larger of the two stars has a mass of about 0.68 times that of the Sun, and a radius of about 0.64 times that of the Sun. Its surface temperature is about 4,450 Kelvin, and it shines with about 14% of the Sun's luminosity. The smaller red dwarf has a mass of about 0.20 times the Sun's, a radius of about 0.22 times, and a surface temperature of about 3,311 Kelvin. It glows faintly, producing only about half of 1% of the Sun's brightness. Astronomers estimate the age of the Kepler-16 system to be about 2 billion years, less than half the age of our own Sun, which is about 4.6 billion years old, with a surface temperature of 5,778 Kelvin. Kepler-16b orbits the shared centre of mass of its two stars at a distance of about 0.704 astronomical units. An astronomical unit is the average distance from the Earth to the Sun, about 150 million kilometres. This means the planet orbits at nearly the same distance from its stars as Venus does from our Sun. However, because the stars are cooler and dimmer than our Sun, the environment of Kepler-16b is far colder. Scientists believe it is unlikely that the planet formed in its current orbit. Instead, it probably formed farther away and later migrated inward. Interestingly, its orbit is almost perfectly circular, with very little eccentricity, a fact that astronomers still do not fully understand. The habitable zone in the Kepler-16 system, the region where liquid water could exist, stretches from about 55 million to 106 million kilometres from the two stars. Kepler-16b, with its orbit of about 104 million kilometres, lies very close to the outer boundary of this habitable zone. Though the gas giant itself is not a candidate for life, scientists speculate about the possibility of moons around it. If Kepler-16b were to capture or host a large moon, that moon could, in theory, have conditions suitable for life. Researchers at the University of Texas have run simulations suggesting that in the history of the system, gravitational interactions might have caused an Earth-sized planet, originally in the middle of the habitable zone, to migrate outward, where Kepler-16b could have captured it as a moon. If such a moon existed, it could potentially be a world with oceans and perhaps even the right conditions for biology. Other studies considered the possibility of a planet orbiting even farther out at about 140 million kilometres. With a thick atmosphere rich in greenhouse gases like carbon dioxide and methane, such a planet could retain enough heat to keep water liquid, even at that great distance. For moons to remain stable around large planets, there are certain rules of orbital dynamics. One key requirement is that the ratio between the moon's orbital period around the planet and the planet's period around its star must be less than 1 to 9. For example, if a planet takes 90 days to orbit its star, the moon must complete its orbit around the planet in less than 10 days. Simulations suggest that a moon with a period shorter than about 45 to 60 days would remain securely bound to a gas giant like Kepler-16b. If such a moon existed, tidal forces from the planet could help drive geological activity, such as plate tectonics. This would cause volcanic eruptions that release gases into the atmosphere and regulate surface temperatures. These processes could also generate a magnetic field through what is called a geodynamo effect, offering protection against harmful stellar winds and radiation. To maintain an atmosphere similar to Earth's for billions of years, a moon would need to have a density like that of Mars and a mass of at least 7/100ths that of Earth. A strong magnetic field would further help to prevent atmospheric loss. Evidence from our solar system shows that such a scenario is possible. NASA's Galileo spacecraft discovered that Ganymede, Jupiter's largest moon, has its own magnetic field despite being much smaller than Earth, with a mass of only 2.5% of Earth's. LTT 9779b, which is now officially named Quankoa, is one of the most unusual planets ever discovered beyond our solar system. This world is roughly the size of Neptune and circles a sun-like star known as LTT 9779, which also carries the official name Uber. Quankoa stands out among all known planets because of one very striking feature. As of the year 2023, it holds the record for being the most reflective planet we've ever found. The planet was first discovered in the year 2020, when astronomers carefully studied data gathered by NASA's Transiting Exoplanet Survey satellite, more often called TESS. In scientific records, Quankoa is sometimes also labelled as TOI 193b, but its official name is now recognised worldwide. What makes this planet so intriguing is that it belongs to an extremely rare category of exoplanets, found in what astronomers call the Neptunian Desert. This is a region of parameter space where planets the size of Neptune almost never survive, because being so close to their host stars usually strips them of their atmospheres. Yet, Quankoa has managed to endure in this hostile environment. That alone makes it a cosmic curiosity. Quankoa is incredibly bright because it reflects so much of the starlight that falls upon it. Its albedo, which is the scientific term for reflectivity, is measured at about 0.73 plus or minus 0.11. In simpler words, more than 70% of the sunlight that strikes Quankoa is reflected back into space, making it shine like a cosmic mirror. This level of reflectivity is higher than that of any other exoplanet discovered so far. For comparison, Earth reflects only about 30% of the sunlight that hits it. The orbit of Quankoa is breathtakingly short. It completes a journey around its star in less than a single Earth day. Imagine a year that is over before 24 hours have even passed. Because the planet is so close to its star, the surface and atmosphere on its day side become unimaginably hot. Temperatures rise well above 2000 degrees Celsius, far beyond what any material on Earth could withstand. Computer models of Quankoa's atmosphere suggest that it is rich in heavy elements, meaning its gases contain far more metals than those of giant planets like Jupiter. These models also show that thick clouds, possibly made of silicate materials, the same kinds of minerals that make up rocks on Earth, could be drifting across its skies. Being located in the Neptunian desert makes Quankoa even more of a rarity. Astronomers estimate that only about 1 in every 200 stars similar to our Sun hosts a planet with an orbit lasting less than a single day. And among those rare systems, most of the known planets are either giant, hot Jupiters or smaller rocky worlds. Ultra-hot Neptune-like planets such as Quankoa are practically unheard of. Because of this, Quankoa has become a prime target for observation by some of the world's most powerful telescopes, including the Hubble Space Telescope and the James Webb Space Telescope, often called JWST. Using JWST's NIRISS instrument, researchers have detected brilliant white clouds covering parts of Quankoa's day side. Interestingly, these clouds seem to form more on the western side of the planet's illuminated hemisphere. Scientists believe this happens because powerful eastward winds, known as equatorial jets, push heat across the planet. This leaves the western side slightly cooler, which allows clouds made of silicate minerals to condense there. The two main cloud components identified are enstatite, or magnesium silicate, with the chemical formula MgSiO3, and forsterite, or magnesium orthosilicate, with the formula Mg2SiO4. These minerals are essentially the building blocks of rock, meaning that on Quankoa, it literally rains tiny grains of rock dust high in the atmosphere. The same JWST study also found traces of water vapour in the planet's atmosphere. This discovery came from observing a dip in the light spectrum around 1.4 micrometers, a signature feature of water. Temperatures on Quankoa's day side were measured at about 2,260 Kelvin, which equals about 2,000 degrees Celsius. The night side was much cooler, estimated to be below 1,330 Kelvin. This stark contrast between the blistering day and the much cooler night is a dramatic reminder of how extreme the environment of this planet is. However, not all results perfectly align. A study published in the year 2025 suggested that Quanqua's atmosphere cannot be explained as just a simple, cloudy world. Instead, some form of mixing process, perhaps involving powerful winds or unusual chemistry, might be stirring the atmosphere and changing its composition in complex ways. Another study in the same year confirmed that the planet's atmosphere is indeed very rich in metals, and again pointed toward the likely presence of silicate clouds. The story of Quanqua's naming is also worth noting. In the year 2022, the International Astronomical Union, through its Name Exoworlds competition, invited people around the world to suggest official names for certain exoplanets and their stars. LTT 9779b received the name Quanqua, a word from the Ewa language, also called Tunabo, spoken by an indigenous people of Colombia. Quanqua means morning star. Its host star, LTT 9779, was given the name Uba, which in the same language means star, seed, and eye. These poetic names highlight the deep human connection between science and culture, weaving ancient traditions with modern discoveries. When astronomers first confirmed Quanqua in the year 2020, they measured its physical properties and found them equally remarkable. This planet is about 29 times more massive than Earth, and about 4.7 times larger in radius. With its extremely short orbital period of less than 1 day, it became immediately clear that Quanqua belongs to the select group of ultra-hot Neptunes. The Spitzer Space Telescope, another powerful observatory, studied Quanqua and measured its dayside temperature at about 2,305 Kelvin. This translates to about 2,032 degrees Celsius, or 3,689 degrees Fahrenheit. Meanwhile, the Cheops Space Telescope confirmed just how reflective Quanqua is, measuring its albedo at about 80%. In other words, 4/5 of the starlight striking it bounces back into space. Interestingly, even before Quanqua was confirmed, a study in the year 2019 hinted at the possibility of another planet in the same system. This was suggested based on subtle, timing variations in the transits of Quanqua. However, when the discovery paper for Quanqua was published, astronomers looked carefully for such variations and found no evidence of an additional planet. To this day, Quanqua remains the only known world orbiting Uba,